Okay, David, we are live, and it looks like I can no longer stream Twitter without a premium subscription. Um, I let my Twitter subscription lapse because I just didn't think it was worth the money. And one of the things you have to pay for is the ability to live stream to Twitter. So I will not be live on Twitter today, so I will post my stream, and we have a lot to cover today. So I'm making a lot of progress in my metaphysics series, and the last week we finally got to the Royal Society of London, and some of the major names of the founders, people around. Uh, Francis Bacon, who was basically the precursor to the Royal Society, but passed away before its founding, one of the important people of the creation of the scientific method. Thomas Hobbes, who was rejected membership of the Royal Society. He didn't know geometry, tried to square the circle, but was closely connected to the Cavendish family and somewhat one of the fathers of empiricism. And in the time of the creation of the Royal Society, we looked at our first female in the series, Margaret Lucas Cavendish, who brother and husband were both connected to the founding of the Royal Society of London, and she was somewhat a little bit of a philosopher and amateur scientist herself, a lot of writing. So we covered that briefly. Actually, that one was quite long, and even a little thoughts on feminism, and possibly one of could be considered the creators of science fiction. And then we looked at Robert Boyle, who was one of the founders of the Royal Society, who also had a lot of thoughts on religion, best known for the relationship between pressure and volume, and one of the original experimentalists. So, Hooke, who also was one of the founders, he was the first president of the Royal Society before Newton, doesn't have his own entry on the Royal Society because on the Stanford Encyclopedia, because it's mostly dealing with philosophy. And although Hooke was a great experimentalist and had a lot of back and forth with Newton, he didn't necessarily make any contributions to philosophy. And then last but certainly not least, probably most important, we looked at Isaac Newton, and that largely covered his biography and an overview of his work. But Newton, probably the most important figure, possibly the single most important figure we're going to cover in this series. And I've talked about Newton at length with like Galileo, Descartes, Newton, where Newton solidifies the basis for modern science. And what I started the series with the modern logicians of Bertrand Russell, Frege, um, Wittgenstein, people who try to reduce science and philosophy to logical notation. So largely that's an outgrowth of Newton, with the Galileo trying to create universal scientific laws expressed in mathematics, to Descartes with the dualism from the former hylomorphism, but Descartes creating the algebra connected to geometry in the large mathematics, capable of creating these universal uh, mathematical laws to define universal natural law. However, Descartes failed in correctly identifying any of these universal natural laws, and Newton takes it to the next step. And we'll see at length Newton does something that goes against uh, Descartes and Leibniz and most of the continental idealists. We've also talked quite a bit about idealism. We'll talk about it more. Probably the next episode, we'll go back to the French when we'll look at Descartes and Gassendi and Mellenbrock and Arnauld, some of the contemporaries on the continent of the same time, but their understanding of space, time, and motion um, largely wanting to reject, mostly according to theological grounds, that there could be such a phenomenon as empty space. So Newton, in order to create these universal scientific laws, um, necessitates um, what we'll call absolute space and absolute time, where there's just a phenomenon of this XYZ coordinate system that's absolute, uh, and time as an absolute and just a forward ticking of time that is not connected to any single phenomenon. And eventually that gets changed with Einstein and general relativity, and hopefully we'll get to that. But like the precursor of why Newton was so important at the time to um, leading to modern science and almost all current materialism. Although Newton was not a materialist, so like Descartes kind of sets the ground for future materialism, because basically saying, well, science tells you how the heavens go and religion tells you how to get to heaven. And so to say, science describes the material realm and religion, spirituality describes the spiritual realm. But eventually the necessity for the spiritual realm becomes eliminated. So what Descartes started by largely, seeing what happened to Galileo and saying he's not going to encroach upon the church or any of the spiritual function, he's just going to try to define a system to explain physical phenomenon, eventually is the downfall of religion and spirituality, because science, material explanations come to be accepted to explain what at once had been considered spiritual phenomenon, namely the mind. But we'll get to that at a much later point. And Thomas Hobbes is one of the first important materialists, as is Cavendish, who, these early conceptions that mind comes from the brain and is internally materially connected, as opposed to being part of the spiritual realm. So Newton doesn't have that much metaphysics or various things connected to that topic. However, um, however, uh, Newton is extremely important for modern philosophy, and especially science and the philosophy of science. So I will go in depth. Hopefully, I'll be able to finish today. This could be as much as like 8 hours. I have a lot to cover. You'll all hear from the Plato Encyclopedia. So first we'll look at um, Newton's philosophy. Then we'll look at a little background, absolute and relational space in motion and classical theories, starting from Aristotle, Descartes, Newton. We'll look at Leibniz, and a little bit of a precursor leading into modern forms of quantum mechanics, general relativity. Then we'll look in depth at Newton's view of space-time and motion. Then we'll do a deep dive into Newton's Philosophy Naturalis Principia Mathematica, the Principia, his main writing that he's most well known for. And then we will look at Hume's Newtonianism and anti-Newtonianism, and how David Hume adapted the teachings of Isaac Newton in forming somewhat the modern empiricism and skepticism. Because we'll see there's a lot of uncertainty in what Newton meant, or various interpretations, and Newton is sometimes given more credit than possibly he deserves, because like Newton did make some mistakes. And as we saw in last week's stream, that our modern conception of Newtonian mechanics was not actually the system devised by Newton. And although Newton was the founder of a lot of these ideas, the formal conception of Newtonian classical mechanics was largely founded on the continent through later mathematicians like Huygens, Bernoulli, Huygens, and Euler. So the form of Newton's three laws and the differential equations that we learn about it today is um, largely the product of Euler. And my dad has the original, yeah, I mean, copies of Euler's. I mean, I think he wrote in German. Uh, Newton's still writing in Latin, and so Euler probably also wrote in Latin. Um, but our modern conception, like when we take physics and calculus in school, that wasn't the physics and calculus created by Newton. It was largely the system created by Euler, and there's later adaptations. But still, Newton is largely given credit and created, the system, the precursors of calculus and modern physics, and the different the integral and derivative relationship. So, Mr. Boston, good to see you. Um, yeah, I stuck only, staying in my lane of my research. So if people want to reach out and speak to me about Judaism, I'm willing to do it on my week in review. I don't even really promote my week in review, so I'm getting very small numbers relatively. So yeah, I think it's just tough to have reach. So I would just stick to my research. So, and I'm not even trying to connect this just as is. I'm not, like connecting this to other things or its implication to other thoughts. Eventually, I'll do that at a different time. But just a deep dive today into Newton, and we won't be covering any other topics. So let me just pour myself a little more drink. Yeah, I would be more interested in reaching a small group of people that take these ideas seriously and want to discuss them. I saw like that guy Yuda Amslog is kind of taking over these JQ debates, and they're pretty vicious and unfriendly. So a few people that have wanted to have largely respectful conversations, and some of them in big names, even like Adam Green and um, Keith Woods, Daniel Iquachu. I would continue to discuss with these things, but I'm not, like, it's kind of a business and self promotion and e-celebrity, so I'm just trying to avoid that. And I would be more interested, like active inference, a small group of people interested in these ideas, and because changing the minds of the masses is a difficult thing and a different venture, especially if you're going to put yourself forward to do that. And as of now, besides for independent scholarship that might occasionally um, be called for, which I'm happy to give, there's really no venue for me to do that. So let's jump right in. Um, this is probably at least 7 hours worth of reading, maybe even 8 hours. If I have strength, I'm going to do the whole thing. If not, I will separate it into today and tomorrow I will do Newton's Principia and Hume's Newtonianism and anti-Newtonianism, and just do the first three today. So let's see how long it takes. A lot of these are extremely long, and I'm not sure how long it's going to take to read. So let's jump right in. Newton's philosophy. Isaac Newton, 1642 to 1727, lived in a philosophically tumultuous time. He witnessed the end of the Aristotelian dominance of philosophy in Europe, the rise and fall of Cartesianism, the emergence of experimental philosophy, and the development of numerous experimental and mathematical methods for the study of nature. Indeed, he helped to develop many of those methods. Newton's contributions to mathematics, including the co-discovery with Leibniz of what is now we now call the calculus, and to what we call physics, includes both its experimental and theoretical aspects, will forever dominate discussions of his lasting influence. His impact on the development of early modern philosophy was also profound. Indeed, it is difficult to grasp the history of philosophy in the late 17th and early 18th centuries without considering Newton's roles. His engagement with Cartesian ideas and methods early in his life was just as significant to the transformation of philosophy in the 17th century as his debates with Leibniz were to setting of the agenda of philosophy in the 18th. Obviously, Newton is not part of the traditional philosophy canon of the period. The fact reflects an anachronistic approach to the history of modern philosophy that we have inherited from the French and German scholars in the 19th century. During the height of the Enlightenment, Newton was always characterized as a canonical philosopher. For instance, he plays a leading role in the very first modern history of modern philosophy, Johann Jacob Bruckner's History of Critical Philosophy of 1744. Every major Enlightenment thinker, from Diderot to D'Alembert to Kant, was influenced by Bruckner's account of modern philosophy. In tandem, numerous works on Newton's philosophy and his philosophical discoveries were published throughout the 18th century in every major European language. By the early 19th century, however, a separation between science and philosophy had been effectuated, which led to Newton's shunting into the science canon. Recent scholarship has challenged this conception of the canon. Moreover, Newton engaged with or influenced many of the standardly canonical philosophers of the early modern era, including Descartes, Locke, Berkeley, Hume, Leibniz, and Kant. His influence on early modern philosophy is a rich topic. Okay, so this section has 7 parts. Placing Newton in the history of natural philosophy. Traditionally, Newton would be characterized as a mathematician for his work on the calculus and as a scientist for his work in physics. His celebrated talent in mathematics is perhaps not equaled not only by his profound theorizing concerning the physical world, but also his influential experimental methods. Indeed, Newton is remarkable for the fact that his work as a theoretician is matched by his work as an experimentalist. Either aspect of his oeuvre would be sufficient to secure his place in the history of modern science. So, in the popular imagination and even in history books, Newton is seen one of the greatest scientists of the modern period, on par with few others, perhaps Darwin or Einstein. This view will continue to dominate our understanding of Newton in the 21st century. If we attempt to understand Newton's work from a historical point of view, however, a more complex conception emerges. While Newton published his principal works, he was not contributing to a well-established field. He was helping to create modern mathematical physics. This meant that few of his ideas, methods, or approaches, whether in mathematics or experimental physics, could be taken for granted. From his first papers in the early 1670s on optics until his last days working on the third and final edition of his magnum opus of the Principia, decades later, philosophers, mathematicians, and experimenters challenged Newton's approach. This frequently upset Newton, who had a famous lifelong aversion to intellectual debate and controversy, but in a sense it helped to ensure the importance of Newton's idea for philosophy. Obviously, Newton never wrote a philosophical text on the order of Descartes' Meditation, Locke's Essay, or Spinoza's Ethics. He never produced what the luminaries who studied him would have called a system of philosophy, but the intense controversies produced by his mathematical, empirical, and philosophical methods and ideas continually prompted him to broach philosophical topics. As a result, he was widely considered a leading philosopher throughout the Enlightenment. In the first modern history of philosophy, Bruckner's History Critical Philosophy, Newton plays a central role in the discussion of the modern era. He is also a central figure in D'Alembert's discussion of the emergence of modern science and philosophy. Newton is listed along with Bacon, Descartes, Locke, and Leibniz as a key figure in the preliminary discourse. The 18th century tendency to discuss Newton's philosophy rather than science may have an odd ring to modern ears. In this case, however, the evolution of the English language tracks a substantive intellectual development. As a matter of historical fact, the category of scientist, along with that word in English, is a 19th century invention. Specifically, at a meeting of the British Association for the Advancement of Science in June 1833, the Cambridge philosopher William Whewell, who we covered in the series already, coined the word scientist. Whewell said that just as the practitioners of art are called artists, the practitioners of science ought to be called scientists, indicating that they should no longer be called philosophers. Indeed, before the early 19th century, people like Newton were called philosophers, or more specifically, natural philosophers. During the 17th century and well into the 18th century, at least until 1750, if not later, figures like Newton worked within the centuries-old tradition of natural philosophy. The modern disciplines of physics, chemistry, biology, and so on had not yet been formed. The word physics in English, physique in French, and physica in Latin were often used but had a very broad meaning, like natural philosophy. Philosophers who studied nature investigated such things as planetary motion, the nature of matter, and the possibility of a vacuum, but they also discussed many aspects of human beings, including the psyche and how nature reflects its divine creator. As the title of Newton's magnum opus, Mathematical Principles of Natural Philosophy, suggests, he intended his work to be in a dialogue with Descartes' Principles of Philosophy 1644. Descartes' Principles is a complex text that includes discussions of everything from the laws of nature to the nature of God's causal influence on the world. Descartes had famously promised that his physics required nothing more than the principles of geometry and pure mathematics. Although Descartes was a great mathematician, the author of a major work in geometry in 1637, Newton thought nonetheless that he had not lived up to this promise. So he would assuredly introduce mathematical principles for natural philosophy, just as Descartes had sought to replace Aristotelian or scholastic methods and doctrines in natural philosophy. Newton sought to replace Descartes. It is therefore more historically accurate and more illuminating to interpret Newton within the historical stream of natural philosophy. As it is well known, natural philosophy in the Aristotelian tradition of the 13th through the 16th centuries involved the analysis of Aristotle's idea about the natural world, especially within the Christianized context of the medieval period. Philosophers studying nature were often actually studying texts such as commentaries on Aristotle rather than conducting experiments or engaging in observations, and they often did not employ mathematical techniques. Traditionally, natural philosophers in Aristotelian circles were not convinced of a mathematical discipline, unlike, say, optics or astronomy. Instead, it focused especially on the nature of objects and on causation. In the 17th century, natural philosophers from Galileo, Boyle, Descartes, and Newton began to reject not only the doctrine of the Aristotelians, but their techniques as well, developing a number of new mathematical, conceptual, and experimental methods. Newton respected Descartes' rejection of Aristotelian ideals, but argued that Cartesians did not employ enough of the mathematical techniques of Galileo or the experimental methods of Boyle in trying to understand nature. Of course, these developments have often been regarded as central to the scientific revolution, despite the centrality of these changes during the 17th century. However, the scope of natural philosophy had not dramatically changed. Natural philosophers like Newton expended considerable energy trying to understand the nature of space, time, and motion, but they regarded that endeavor as a component of an overarching enterprise that also included an analysis of the divine being. Newton was a natural philosopher. Unlike Descartes, he was not a founder of modern philosophy, for he never wrote a treatise of the order of meditations. Nonetheless, his influence on philosophy in the 18th century was profound, extending well beyond the bounds of philosophers studying nature, encompassing numerous figures and traditions in Britain, on the continent, and even in the New World. Newton's influence has at least two salient aspects. First, Newton's achievement in the optics and in the Principia was understood to be of such philosophical import that few philosophers of the 18th century ignored it. Most of the canonical philosophers on this period sought to interpret various of Newton's epistemic claims within the terms of their own systems, and many saw the coherence of their own views with those of Newton as a criterion of philosophical excellence. Early in the century, Berkeley grappled with Newton's work on the calculus in the Annals 1734 and with his dynamics in De Moto 1721, and he even mentioned gravity, the paradigmatic Newtonian force, in his popular work, Three Dialogues between Hylas and Polonius, 1713. While Berkeley lists what philosophers take to be the so-called primary qualities of material bodies in the dialogues, he remarkably adds gravity to the more familiar list of size, shape, motion, and solidity, thereby suggesting that the received view of material bodies had already changed before the second edition of the Principia had circulated widely. Remarkably, in the same year, Roger Coates, the editor of the second edition of Newton's Principia, had argued in his editor's preface that gravity should indeed be considered a primary quality, along with the more familiar mechanics properties that had been subject of so much discussion in previous years. Newton himself approached the topic more cautiously. For his part, Hume interpreted Newtonian natural philosophy in an empiricist vein and noted some of its broader implications in the Treatise of Human Nature, 1739, and Inquiry Concerning Human Understanding, 1750. Newton's work also served as an impetus for the extremely influential correspondence between Leibniz and Newtonian Samuel Clarke early in the century, a correspondence that proved significant even for thinkers writing towards the century's end. Unlike the vis viva controversy and other disputes between the Cartesian and the Leibnizians, which died out in the middle of the century, the debate between the Leibnizians and the Newtonians remained philosophically salient for decades, serving as the impetus for Émile du Châtelet's influential work during the French Enlightenment, Foundations of Physics, 1740, and also as one of the driving forces behind Kant's development of the critical philosophy during the 1770s, culminating in the Critique of Pure Reason, 1781. In addition, Newton's work spawned an immense commentarial literature in English, French, and Latin, including John Keel's Introduction to Natural Philosophy, 1726, Francesco Algaroti's Newtonianism for the Ladies, 1738, Henry Pemberton's A View of Sir Isaac Newton's Philosophy, 1728, Voltaire's Elements of the Philosophy of Newton, 1738, William Gravisende's Mathematical Elements of Natural Philosophy, 1747, Colin Maclaurin's An Account of Sir Isaac Newton's Philosophical Discoveries, 1748, and many more besides. Moreover, two subsequent continental editions of Newton's text contain substantial philosophical engagements, not only with his own ideas, but those of his potential rivals like the great mathematician Johann Bernoulli and also Leibniz, the famous Jesuit or Geneva edition of the Principia Mathematica, published by Fathers Lesueur and Jacquier in 1739 to 44 in 3 volumes, engaged substantially with Leibnizian ideas, and Émile de Châtelet wrote an extensive analytical commentary as part of her French translation of the Principia, published posthumously in 1759. Part of the idea was to translate Newton's old geometric approach to physics into a new language of analysis, a project that was intertwined with numerous philosophical issues. Newton's ideas and methods in mathematics, physics, and philosophy therefore continued to be of substantial importance well into the Enlightenment. A second aspect of Newton's influence involves thinkers who attempted in one way or another to articulate, follow, or extend the Newtonian method in natural philosophy when treating issues and questions that Newton ignored. Euclidean geometry and its method were seen as fundamental epistemic models for much of 17th century philosophy. As is well known, Descartes' meditation attempts to achieve a type of certainty he likens to that found in geometry, and Spinoza wrote his Ethics according to the geometric method. Propositions deduced from axioms in Euclidean geometry were seen as the paradigm cases of knowledge. We might see Newton's work as providing an 18th century philosophy with one of its primary models and with a series of epistemic exemplars as well, but part of philosophy's task was to articulate precisely what the new Newtonian method involved. David Hume is perhaps clearest about the aspect of Newton's influence. In his treatise of 1739 has the subtitle, An Attempt to Introduce the Experimental Method of Reasoning into Moral Subjects, and there can be little doubt that he meant, at least in part, the method of optics and Principia. Indeed, as Hume's text makes abundantly clear, various 18th century philosophers, including not only Hume in Scotland and Jean-Jacques Rousseau on the continent, were taken to be or attempted to become the Newton of the mind. For Hume, this meant following what he took to be Newton's empirical method by providing the proper description of the relevant phenomenon and then finding the most general principles that account for them. Of course, one aspect of Hume's work is to provide an analysis of the concept of causation that is far more extensive than anything found in Newton, which has a substantial impact on what counts as an account of phenomenon. This method would allow us to achieve the highest level of knowledge attainable in the realm of what Hume calls matters of fact. Despite the influence of Newton's method on 18th century philosophy, it is obvious that the Principia's greater impact in the 18th century is to have affected a branching within natural philosophy that led to the development of mathematical physics on the one hand and philosophy on the other. And yet to achieve an understanding of how Newton himself approached natural philosophy, we must carefully bracket some historical developments that did not solidify until sometime after 1750, a generation after Newton's death. Indeed, if we resist the temptation to understand Newton as working within a well-established discipline called mathematical physics, if we see him instead as a philosopher studying nature, his achievement is far more impressive, for instead of contributing to a well-founded field of physics, he had to begin a process that would eventually lead aspects of natural philosophy to be transformed into a new field of study. This transformation took many decades, involving a series of methodological and foundational debates about the proper means for obtaining knowledge about nature and its processes. Newton himself not only engaged in these debates from his very first publication, Optics, in 1672, but his work on both optics and in the Principia generated some of the most significant methodological discussions and controversies in the late 17th and early 18th century. These debates concern such topics as the proper use of hypothesis, the nature of space and time, the best understanding of the forces of nature, and the appropriate rules for conducting research in natural philosophy. Newton's achievement was in part to have vanquished both Cartesian and Leibnizian approaches to natural philosophy in the latter 18th century, and indeed much of the 19th. Physics was a Newtonian enterprise more than anything, but this achievement from Newton's own perspective involved an extensive lifelong series of philosophical debates. Those debates focused on numerous substantive issues, but also included extensive discussions on the proper methodology in natural philosophy. Methodology. The optics debate before the 1670s. Philosophers have long known about the aspect of Newton's work that are salient for understanding debates of the early modern period. For instance, no history of debates about the ontology of space and time would exclude a discussion of Newton's famous conception of absolute space. Similarly, any discussion of the role of hypothesis and philosophical reasoning would mention Newton prominently. These aspects of Newton's work continue to be significant in contemporary scholarship, but the scope of the discussion of Newton has greatly expanded, encompassing the whole of his intellectual life. This is especially evident in the discussion of Newton's earliest published work, which is in the field of optics. In at least three relevant respects, Newton's early work in optics, which was published in the Philosophical Transactions of the Royal Society beginning in 1672, set the stage for the principal themes of his long career in natural philosophy. He remained active well into his 70s. Firstly, Newton's letter to the Society's secretary Henry Oldenburg, often called the New Theory about Light and Colors, generated an immediate, extensive, and protracted debate that eventually involved important philosophers such as Robert Hooke in Britain and Christian Huygens in Gottfried Wilhelm Leibniz and Ignatius Parties on the continent. Newton consistently regarded these figures not merely as disagreeing with his views, but as misinterpreting them. This experience helped to shape Newton's famous and lifelong aversion to intellectual controversy, a feature of his personality that he often mentioned in letters, and one he would never outgrow. Secondly, because Newton regarded himself as having been deeply misinterpreted by his critics, he had recourse to meta-level or methodological discussion of the practice of optics and of the kinds of knowledge that philosophers can obtain when engaging in experiments with light. The novelty and power of Newton's work in the Principia years later would eventually generate similar controversies that led him to analogous kinds of methodological discussions of his experimental practice within natural philosophy and of the kinds of knowledge that one could obtain in the field using either experimental or mathematical techniques. From our point of view, Newton's science was unusually philosophical for these reasons. Thirdly, and finally, in his earliest optical work, Newton began to formulate a distinction that would remain salient throughout his long intellectual career, contending that a philosopher must distinguish between a conclusion or a claim about some feature of nature that is derived from experimental or observational evidence and a conclusion or claim that is mere hypothesis, a kind of speculation about nature that is not or not yet anyway so derived. Newton's much later proclamation is the second edition of the Principia, 1713, hypothesis non fingo, I find no hypothesis, would infuriate his critics just as much as it would prod his followers into making the pronouncements of a central component of newly emerging Newtonian method. The field of optics has its origins in the ancient Greek period, when figures like Euclid and Ptolemy wrote works on the subject, but often focused primarily on the science of vision, analyzing the visual rays that were sometimes thought to extrude from the eye, enabling it to perceive distant physical objects. In the early modern period, Kepler and Descartes each made fundamental contributions to the field, including the discoveries of the inversions of the retinal image and an explanation of refraction. Newton's work helped to shift the focus of optics from an analysis of vision to an investigation of light. In New Theory about Light and Colors, published in the Philosophical Transactions in 1672, Newton presented a number of experiments in which sunlight was allowed to pass through one or two prisms in order to probe some of its basic features. The paper recounts a number of experiments that Newton says he had conducted several years earlier, but what precisely counts as a feature of light? Numerous philosophers during the 17th century, including Hooke and Huygens, developed a doctrine concerning the fundamental physical nature of light in an answer to the question, is light a stream of particles or corpuscles or a wave? Both Hooke and Huygens were wave theorists. This question obviously continued to have relevance into the 20th century when wave-particle duality was discovered. In his experiments with prisms, however, Newton apparently sought to investigate something else, what he calls the celebrated phenomenon of colors. Newton's various prism experiments, which he describes in considerable depth, suggested what he called the doctrine that he expresses in 13 consecutive numbered propositions. Including these propositions are the following claims about features of rays of light. First, the rays of light that emerge when sunshine passes through the prism exhibit various colors. Second, these colors differ in their degrees of refrangibility, which means that they exhibit and retain an index of refraction even when they are passed through a second prism. Third, these colors or colorful rays are not modifications of sunlight itself, but are original and connate properties of it. And fourth, these facts mean that although ordinary sunlight appears white or perhaps colorless to our perception, it actually contains numerous colors within it, which can be experimentally revealed. This final point suggests in turn that from Newton's point of view, colors are not solely perceived or even perceptible aspects of physical objects. They can be conceived as of hidden features of light which cannot be perceived directly under any ordinary circumstances. The physical influence of the prism is required for them to become perceptible. From a contemporary point of view, Newton's 1672 paper exhibits an intriguing blend of experimental evidence and philosophical argumentation. The latter hinges on Newton's interpretation of the concept of a property of equality, as the following passage, which follows the doctrine expressed in 13 propositions, tellingly reveals. These things being so, it can be no longer disputed whether there be colors in the dark, nor whether they can be qualities of the object we see, nor perhaps whether light be a body, for since colors are the qualities of light, having its rays for the entire and immediate subject, how can we think that ray qualities also, unless one quality may be the subject and sustain another, in which effect is to call it substance? We would not know bodies for substances were it not for their sensible qualities, and the principle of those beings now found due to something else, we have as good a reason to believe that to be a substance also. Newton seems here to be arguing as follows: since rays of light have colors as basic features, we should regard these colors as qualities or properties of the rays, despite the fact that these properties are imperceptible under any ordinary circumstance. But doing so requires us to think of the rays as bearers of qualities, which is to say, as substances in their own right. And if rays or of light are substances, this means that we cannot also think of them as qualities or properties of anything else. The last point follows from a widely accepted notion of substance at the time, one easily found in Descartes, that substances are those items that can independently of other items. Whether they can exist independently even of God is a further question that we could ignore here. And if we cannot think of rays of light as properties or qualities, then they are not waves, for waves are features of some medium. Think of waves on the surface of a lake. Newton concludes light is a stream of particles. He does not use the word perhaps to hedge a bit here. He does use the word perhaps to hedge a bit here. Clearly, philosophical argumentation is a significant aspect of Newton's reasoning in this paper, as are various philosophical concepts. It is intriguing to ponder the question, what overall conception of sensible qualities does Newton presuppose in this piece? If a ray of sunlight passes through my window, the fact that it appears white to me does not undermine Newton's view, or so he thinks, that the ray actually contains a series of colors as its qualities. Are these qualities sensible if their presence can be detected only through the use of one or more prisms, but never through the inspection of the sunlight through ordinary means? Unaided perception glasses, a magnifying glass. These are apt to strike us as canonical philosophical problems. Newton's line of argument quoted above became one of the centerpieces of the debate that his paper generated. In some parts of the paper, when Newton wrote of the rays of light, he had evidently intended to remain neutral on the question of whether the rays are particles or waves. This is remnant of the ancient Greek practice of avoiding physical discussions of visual rays. But then towards the paper's end, Newton added his new line of argument, which employed some philosophical analysis together with some experimental evidence to support the conclusion that rays of light cannot be waves at all. Newton's critics pounced. This led to the first problem he encountered in response to his paper. What he calls the theory of light and colors was not merely rejected, but rather immediately misunderstood, at least from his own perspective. Just days after Newton's paper was read at the Royal Society, Robert Hooke responded with a detailed letter to Oldenburg. In the first few sentences, Hooke indicates that from his point of view, Newton's hypothesis of saving the phenomenon of colors essentially involves the contention that rays of light are particulate rather than wave-like. Hooke argues, in contrast, that light is nothing but a pulsar motion propagated through an homogeneous, uniform, and transparent medium. That is, he argues that light is indeed wave-like. He makes it perfectly clear, moreover, that his hypothesis, the name did not carry a negative connotation in his work, can save the phenomenon of colors just as well as Newton's, which is to say the hypothesis is compatible with the experimental evidence Newton had gathered. Evidently, the line of argument in the passage quoted above caught Hooke's eye. Among philosophers, he was not alone. In a letter to Huygens explaining Newton's theory of light, Leibniz writes that Newton takes light to be a body propelled from the sun to the earth, which, according to Leibniz, Newton takes to explain both the differential refrangibility of rays of light and the phenomenon of colors. Since Newton had employed the concept of substance, quality, and sensible quality when concluding his paper that light is presumably particulate, we are apt to regard the paper as contributing to important discussions within philosophy. After the extensive correspondence and controversy generated in response to Newton's early optical views and experiments, he often threatened to avoid engaging in mathematical and philosophical disputes altogether. He insisted to friends and colleagues that he found intellectual controversy unbearable, but he never followed through with his threat to disengage from discussions in natural philosophy, sending many important letters throughout his long intellectual career. Newton's relations to Cartesianism. Like many philosophers who had worked in the wake of Galileo and Descartes, it seems that Newton never extensively analyzed Aristotelian ideas about nature. He would have encountered such ideas in the curriculum of Trinity College, but there is not much evidence that he took them seriously. Instead, he focused on the modern thinkers that enterprising young students were told to read outside of the standard curriculum. And in England in Newton's day, the greatest modern philosopher of nature was thought to be Descartes. There was substantial evidence that Newton took Descartes' ideas very seriously and expended considerable energy thinking them through and eventually coming to criticize them. Some of the evidence comes from the manuscript that was first transcribed and published in 1962 by the great historian of science, Mary Bowes Hall and Rupert Hall. The untitled manuscript, now known as of gravitation, after its first line, has been the subject of extensive discussions over the past 50 years because it indicates the depth of Newton's interest in Cartesian ideas in metaphysics and natural philosophy. Despite its importance to contemporary understanding of Newton's relation to Cartesianism and much else besides, de gravitatione is not without its problems. First and foremost, the manuscript lacks a date, and there's no scholarly consensus regarding its precise provenance. Second, the manuscript was never finished, so it's difficult to assess its relationship with Newton's mature thinking and philosophy. Finally, the manuscript was not published during Newton's lifetime, so there are questions about whether it represents his considered views. Despite these facts, the text contains a treasure trove of arguments concerning Cartesian ideas. For instance, it dispels the easily formed impression that Newton sought in the Principia to undermine Leibnizian concept of space and time, as his defender Samuel Clarke would attempt to do later in the correspondence of 1715 and 16. Although Leibniz did eventually express what became the canonical early modern formulation of rationalism concerning space and time, this view roughly that space is nothing but the order of relations among physical objects and time nothing over and above the succession of events involving those objects. And although Newton and Clarke were highly skeptical of such a view, it is misleading to read the Principia through the lens provided by the later controversy with the Leibnizians. Newton's extensive attempt in De Gravitatione to refute Descartes' conception of space and time in particular indicates that the scholium should be read as providing a replacement for the Cartesian conception. That is, Newton had a Cartesian and not a Leibnizian opponent primarily in mind when he wrote his famous articulation of absolutism concerning space and time. Unlike questions about Newton's method and his apparent deviation from the norms established by mechanist philosophers like Descartes and Boyle, Newton's conception of space and time, along with his view of the divine being, do not immediately engender a philosophical debate. It was Leibniz more than any other philosopher who eventually succeeded in fomenting a philosophical debate in which the Newtonian conception of space, time, and the divine would play a central role. But Leibniz's philosophical views were relatively unknown when Newton first formed his conception. To the young Newton writing the Principia, Leibniz was another mathematician and not yet a contributor to natural philosophy. Instead, it was Descartes' view of space, the world, and God, which he pondered in his youth and eventually came to reject. So let's make sure I posted so just forgot to post the stream. Thank God to everybody watching. Just forgot to post the stream, so let me do that real quick. Appreciate everybody watching. Sorry for the interruption. Okay, sorry about that. Newton took special interest in the Cartesian view of space and body and in related views concerning the causal relations between minds and bodies and between God and the bodies that constitute the natural world. Like many of Newton's contemporaries in Cambridge in those days, he encountered these Cartesian views within the context of Henry Moore then famous discussion of Cartesianism, a term coined by More himself, beginning with his correspondence with Descartes in 1648 and continue with a series of publications in the later years, many of which Newton owned in his personal library. More argued that Descartes had made two fundamental mistakes. Firstly, wrongly contended that extension and matter are identical and that the world is therefore a plenum. And second, he mistakenly believed that God and the mind were not extended substances, which made their causal interactions with such substances mysterious. Just as Princess Elizabeth of Bohemia had raised fundamental objections to Cartesian dualism, in the early 1640s, More raised similar objections against the Cartesian view of the divine a few years later. Descartes agreed with More, suggesting that God can act anywhere on law if he so chooses, and came very close to accepting More's contention that such a view entails that God must be present within the world wherever he in fact chooses to act. For how could God part the Red Sea? Suggested More, unless God were present precisely where the Red Sea is located. Of course, More argued that God is not made of parts, cannot be imagined, and cannot be affected by the causal activity of material bodies. The causal arrow flows only in one direction, but More concluded that God is extended in his own way. If one fixes Descartes' two basic mistakes, one obtained what More regarded as a proper philosophical view. Space is distinct from matter because it is extended but penetrable, whereas matter is extended but impenetrable, and in tandem, all substances are extended, but whereas some, such as tables and chairs, are impenetrable, others, such as the mind and God, are penetrable and therefore not material. Newton was deeply influenced by both More's criticisms of Descartes and his positive philosophical conception of space and the divine. In a number of texts, including the Gravitatione, the famous discussion of space and time, in the Scholium to the Principia, and the discussion of God in the General Scholium, Newton made his general Morean attitude perfectly clear. He rejected the Cartesian identification of extension and matter, arguing that space itself exists independently of material objects and their relations, and he contended that all entities, including the human mind and even the divine being, are extended in the sense that they have spatial locations, even if they are extended in ways that distinguishes them from ordinary material bodies. In Newton's hands, space became a fundamental concept of natural philosophy, an attitude that is foreign to Cartesians, as Newton puts in his famous passage from De Gravitatione. Space is an affection of a being just as a being. No being exists or can exist which is not related to space in some way. God is everywhere. Created minds are somewhere, and body is in the space that it occupies. And whatever is neither everywhere nor anywhere does not exist, and hence it follows that space is an emanative effect of the first existing being. For if any being whatsoever is posited, space is posited. Hey, Memes, God bless. Good to see you. Appreciate it. Been a while. Thanks for tuning in. Space is fundamentally a fundamental concept, in part because Newton not only conceives of it as an independent of objects and their relations, but because he argues that every entity must somehow connect with space in some way. For Newton, then, if one follows the Cartesians and thinks of the mind or of God as existing without any spatial location, as existing either beyond the natural world or somehow outside of it, then that is equivalent to conceiving of them as non-existent. Newton does not shy away from making this conception of the divine explicit in his public writings, despite the fact that it was anathema to his Cartesian and Leibnizian contemporaries. In the General Scholium to the Principia, which was added to the second edition of the text in 1713, for instance, he famously writes of God: he endures always and is present everywhere, and by existing always and everywhere, he constitutes duration in space. Since each and every particle of space is always, and each and every indivisible moment of duration is everywhere, certainly the Maker and Lord of all things will not be never or nowhere. God is one and the same God always and everywhere. He is omnipresent, not only virtually but also substantively, for active power cannot subsist without substance. For Newton, just as bodies are present in some spatial location, God, an infinite being, is present throughout all the space, throughout all of time. There could not be a clear expression of agreement with More in his debate with the Cartesians concerning the substantial presence of the divine within space. Newton also took issue with the Cartesian idea about motion. His rejection of Cartesian views of space and his embrace of space as a fundamental concept in philosophy following More's influence aligns with his famous discussion of space and time in the Scholium that follows the opening definitions in the Principia. The text influenced nearly every subsequent philosophical discussion of space and time for the next 3 centuries, so its contours are well known. In Principles of Psychology of 1644, Descartes had distinguished between the ordinary and the proper view of motion. Whereas the ordinary view presents motion of a body's change of place, the philosophers know that, properly speaking, motion is a body's change of relations to the bodies that surround it. Recall Descartes' plenum. Newton contends in De Gravitatione that this idea of proper motion, according to which the motion of a body is at least partially a function of its relations to other bodies, is in tension with Descartes' own laws of nature. Also presented in the Principles were according to the conception of what we now call inertia that Descartes presents as his first 2 laws. A body moving rectilinearly will continue to do so unless caused to deviate from its path. Hence, a body's motion is not a function of its spatial relations to other bodies, but rather of its causal relations. That is, according to the first 2 laws, changing a body's spatial relations to other bodies will not alter its rectilinear motion unless a causal interaction occurs. This tension runs deep in the Cartesian system. Newton's Scholium reflects his idea that the concept of motion in the Principia ought to cohere with the laws of motion he endorses. He distinguishes between absolute and relative motion, true and apparent motion, and mathematical and common motion. The same distinctions hold for space, time, and place. The former item in each of these 3 pairings is a concept that coheres with the laws of motion. Newton's first law reflects Descartes' law. It is a new version of the principle of inertia, one incorporating the concept of an impressed force. Since this law indicates that a body's motion is not a function of its spatial relations to other bodies, but rather of whether forces are impressed on it, which replaces the Cartesian concept of causal interactions that involve only impact. Newton cannot rely on a body's motion relative to other bodies if he is to avoid the kind of tension he found in the Cartesian view. Hence, he indicates that a body's true motion, rather than its apparent motion, which depends on our perceptions, or its relative motion, which depends on its spatial relations, is a body's change of position within space itself. That is, true motion should be understood as absolute motion. This means, in turn, that we must distinguish between the common idea of space, according to which space is conceived as involving relations among various objects, like the space of our air, and the mathematical idea are presumably obtained from geometric reasoning that space is independent of any objects or their relations. In order to account for the idea that true motion is absolute motion, then the famous absolute space is postulated. Newton was perfectly well aware that the notion of absolute space is not unproblematic. For instance, if a body's true motion just is its absolute motion, its motion with respect to space itself, then the imperceptibility of space would appear to render any detection of true motion difficult, if not hopeless. Indeed, how would we detect any body's true motion in this view? We might be able to detect a body's changing spatial relations with its nature, but not its changing relation with space itself. Newton's solution to this problem is ingenious. Under certain circumstances, we can detect a body's true motion by detecting its acceleration. We can do so when the body is rotating or has a circular motion, for such motions often have detectable effects. That is one way of understanding what has become one of the most famous, if not infamous, experiments of the early modern period, Newton's bucket. He grew up on a farm in English countryside and often used deceptively simple examples. If one takes an ordinary bucket and fills it with water and then attaches a rope to the bottom of the bucket, one can then twist the rope and let it go in order to make the bucket spin. When the bucket full of water spins around, we can detect the water's acceleration by its changing surface. As Newton puts it, using his law of motion, the water endeavors to recede from the axis of motion, hence its changing surface. But even an observer untutored in physics would grasp the importance of the water's changing surface. That is, perceiving the effect does not depend on the understanding of laws. In this way, despite the fact that Newton wishes to conceive of the water's true motion as its absolute motion within space itself, which cannot be perceived, he shows his reader how they might detect the water's true motion through its effects. Newton provides another simple experiment to illustrate a similar point. If 2 balls are joined together by a rope and then spun around, say, over one's head, then the changing tension in the rope will indicate that the balls are accelerated, since any acceleration is a true motion, although not all true motions are accelerations. Since a so-called inertial motion is not, this case indicates that we can detect a body's true motion even though space itself is imperceptible. In this way, Newton did not merely develop an alternative to the Cartesian view of motion along with the Allied conception of space, he presented a view that could be employed to pick out some of the true motions of objects within nature. Once one has found a true motion, one can then ask what caused that motion. For Newton, as we will see, it is forces that are understood to cause motions. As the last line of the scholium in the Principia indicates, that is one reason that Newton wrote his magnum opus in the first place. Newton's idea of space then fulfilled at least two roles. First, it enabled him to avoid the tension between the concept of true motion and the laws of motion of the kind found in Descartes. Second, it also enabled him to articulate what he took to be God's relation to the natural world. Many regarded his achievement as an important advance over the Cartesian system. However, it would be a mistake to think that Newton vanquished Cartesian ideas within his lifetime. Even in England and certainly on the continent, Cartesianism remained a powerful philosophical force for several decades after Newton published his primary works. Typically, however, Descartes' followers emphasized the importance of his ideas about the mechanisms that pervade nature rather than his views on space and time. In that arena, Newton's views are especially prominent and came in for significant criticism from Leibniz. Methodology, the Principia. Many legends concerning momentous events in history are apocryphal, but the legends of Halley's visit to Newton in 1684 is not. It explains what prompted Newton to write his magnum opus. In August of 1684, Edmund Halley, for whom the comet is named, came to visit Newton in Cambridge in order to discover his opinion about a subject of much dispute in celestial mechanics. At this time, many in the Royal Society and elsewhere were at work on a cluster of problems that might be described as follows. How can one take Kepler's laws, which were then considered among the very best descriptions of planetary orbits, and understand them in the context of dynamical or causal principles? What kind of cause would lead to planetary orbits of the kind described by Kepler? In particular, Halley asked Newton the following question: what kind of curve would a planet describe in its orbit around the sun if it were acted upon by an attractive force that was inversely proportional to the square of its distance from the sun? Newton immediately replied that the curve would be an ellipse rather than, say, a circle. Halley was amazed that Newton had the answer at the ready, but Newton also said that he had mislaid the paper on which the relevant calculations had been made, so Halley left empty-handed. Whether there was any such paper in the subject is a subject of dispute, but he would not be disappointed for long. In November that year, Newton sent Halley a 9-page paper entitled De Motu on Motion that presented the sought-after demonstration, along with several other advances in celestial mechanics. Halley was delighted and immediately returned to Cambridge for further discussion. It was these events that precipitated the many drafts of De Motu that eventually became the Principia Mathematica by 1686. Several aspects of the Principia had been central to philosophical discussion since its first publication, including Newton's novel methodology in the book, his conception of space and time, and his attitude towards the dominant orientation within natural philosophy in his day, the so-called mechanical philosophy, which had important methodological consequences. When Newton wrote the Principia between 1684 and 86, he was not contributing to a pre-existing field of study called mathematical physics. He was attempting to show how philosophers could employ various mathematical and experimental methods in order to reach conclusions about nature, especially about the motions of material bodies. In his lectures presented as the Lucasian professor at Cambridge, Newton had been arguing since at least 1670 that natural philosophers ought to employ geometrical methods in order to understand various phenomena in nature. The Principia represented his attempt to reorient natural philosophy, taking to the direction that neither his Aristotelian predecessors nor Cartesian contemporaries had envisioned. He did not immediately convince many of them on the benefits of his approach, just as his first publications, Optics, in 1672, sparked an intense debate about the proper methods for investigating the nature of light, and much else besides. His Principia sparked an even longer-lasting discussion about the methodology that philosophers should adopt when studying the natural world. This discussion began immediately with the publication of the Principia, despite the fact that its first edition contained few explicit methodological remarks. It intensified considerably with the publication of the second edition in 1713, which contained many more remarks about methodology, including many attempts at defending the Newtonian method. Indeed, many of Newton's alterations in the edition changed the presentation of his methods. Discussions in methodology would eventually involve nearly all the leading philosophers in England and on the continent during Newton's lifetime. In Cartesian natural philosophy, all natural change is due to the impact that material bodies make upon one another's surface. This is reflected in Descartes' first two laws of nature. The concept of force plays little, if any, role. Unlike Descartes, Newton placed the concept of force at the very center of his thinking about motion and its causes within nature. In that regard, his reaction to the shortcoming of Cartesian natural philosophy paralleled Leibniz, who coined the term dynamics, and who obviously regarded force as the fundamental concept in metaphysics as well. But Newton's attitude towards understanding the forces of nature involved an especially intricate method that generally generated intense scrutiny and debate amongst many philosophers and mathematicians, including Leibniz. Newton's canonical notion of force, which he calls vis impressa, or impressed force, is a notion of an action exerted on a body that changes its state of motion. This was a confusing notion at the time. Perhaps it is not difficult to see why that should be so. To take one of Newton's own examples, suppose I hit a tennis ball with my racket. According to Newton, I have impressed a force on the tennis ball, for I've changed its state of motion. We have a reasonably good idea of what the tennis ball is, of what the racket is, and even of what I am. And a Cartesian might wish to stop the analysis there, but what exactly is the force that I impressed on the ball? The ball, the racket, and I are physical things of one sort or another, but this force physical? Is it not physical? It does not seem likely that a force is itself a physical thing in the sense of being a substance, to use a philosophical notion popular in Newton's day. As we saw above in his first optics papers, the reason is that the definition 4 of the Principia, which defines an impressed force for the first time, Newton remarks the force consists solely in the action and does not remain in the body after the action ceases. So when I hit the tennis ball over the net, the force I impressed on it was the action of hitting the ball, or an action associated with hitting the ball, and not a property of me or the ball after the action has ceased. This idea confused many of Newton's readers. By the mid-18th century, the time of Hume's analysis of causation in his treatise and the inquiry, many philosophers started to think that actions and other kinds of events are important items to have in one's ontology, and they often contended in particular that causal relations hold between events, but in Newton's day, philosophers typically regarded objects or substances as the causal relata. Indeed, one actually finds an equivocation between thinking of events and thinking of objects as the relevant causal relata even in Hume. In his inquiry, he first defines a cause so that objects are the causal relata, but then gives an example in which one of the relata is the vibration of a spring. So actions were difficult to analyze, left out of analysis, or conflated with objects. As a result, Newton's conception of force proved confusing even to his most sympathetic interpreters. Moreover, it was unclear to many of Newton's mechanist readers how his forces fit into their rather austere ontological view that material bodies consist solely of properties such as size, shape, mobility, and solidity. Newton did try to clarify his method of characterizing forces if one brackets the question of how to understand forces as ephemeral actions that do not persist after causal interactions have ceased. One can make progress by conceiving of forces as quantities, in particular, since Newton's 8 definitions and 3 laws indicate that forces are proportional to mass and to acceleration, and since mass, or the quality of matter, a concept Newton transformed from its Cartesian origins, where it was understood as a measure of a body's volume, and acceleration are both quantities that can be measured. Newton gives us a means of measuring forces. This is crucial to his method if one thinks of forces as measuring quantities. Moreover, then one can attempt to identify two seemingly disparate forces as, in fact, the same forces through thinking about measuring them. For instance, in the book 3 of the Principia, Newton famously argues in Proposition 5 and its scholium that the centripetal forces maintaining the planetary orbits is the fact that the same as the force of gravity, the force that causes the free fall of objects on Earth. This was a revolutionary idea at the time, one rendered possible in the first place by Newton's way of thinking about forces as quantities. This idea then led Newton to even more revolutionary view in Proposition 7 of Book 3 that all bodies gravitate towards one another in proportion to their quantity of matter. That is, it led him to the idea of universal gravity, a view that shocked many of his continental readers in its boldness. This helped unify what were once called superlunar and sublunar phenomenon, a unification that was obviously crucial for later research in physics. The idea was enabled by Newton's abstract way of understanding forces without conceiving of a forces involving any specific mechanism or type of physical interaction. Newton thought of forces as quantities that are proportional to other features of nature. Despite his evident success in obtaining what we now called the law of universal gravitation. Newton admits he lacks another kind of knowledge about gravity. This lack of knowledge directly reflects an aspect of his abstract characterization of forces. In the general scholium, he reminds his readers that gravity is proportional to a body's quantity of matter, its mass, and reaches across vast distances within our solar system, adding, I have not as yet been able to deduce from phenomenon the reason for these properties of gravity, and do not find hypothesis. With this phrase, one of the most famous in all of Newton's writing, he returned a key theme of his very first optical paper from 40 years earlier, the proper role of hypothesis and of hypothetical reasoning within natural philosophy. Some of Newton's interpreters have regarded this phrase as signaling a strong commitment to the broad doctrine that all hypotheses concerning natural phenomenon ought to be avoided in principle. This interpretation is something coupled with the view that some British philosophers of the late 17th century regarded Cartesianism as overly reliant on hypothesis in reaching conclusions about phenomenon. But this interpretation may be hard to square with Newton's text. For instance, in Scholium to Proposition 96 of Book 1 of the Principia, Newton discusses hypotheses concerning light rays. Similarly, in Query 21 of the Optics, he proposes that there might be an ether whose differential density accounts for the gravitational force acting between bodies. In light of such examples, one could read the general Scholium's pronouncement in this way: a philosopher concerned with explaining some feature of nature, such that the fact that gravity is inversely proportional to the square of spatial separation, rather than, say, the cube, may legitimately entertain and propose hypothesis for consideration, but she may not find the hypothesis in the sense of taking it as having been established either through experiment, observation, or some form of reasoning, including mathematical reasoning. Hence, Newton thinks that he has established the fact that gravity acts on all material bodies in proportion to their quantity of matter, but he has not established the existence of the ether. What then does Newton's slogan, hypothesis non fingo, actually rule out? By the time of the general scholium, Newton was increasingly embroiled in philosophical disputes with Leibniz. After reading a copy of the Principia that Newton had sent him, Leibniz wrote an essay, Tentamen, on the causes of planetary motion for the famous journal Acta Eruditorum, in order to account for the motions of the planetary bodies. In his Tentamen, published in 1689, Leibniz introduces ex hypotheses, the premise that some kind of fluid surrounds and is contiguous to the various planetary bodies, and then argues that this fluid must be in motion to account for their orbits. Newton may have argued that Leibniz had feigned the hypothesis of the vortices, that is, he would have objected to Leibniz's conclusion that there must be vortices in the solar system, as opposed to the suggestion, for instance, that we try to detect their presence through observation of things like comets. A debate between the two philosophers on this score would bring them to the question of the mechanical philosophy, whereas Newton would object to Leibniz's reasoning on methodological grounds. Leibniz would reply that Newton's theory of gravity involved action at a distance, which his vortex hypothesis avoids. Once the Principia was published, Newton had a vexed relationship with the mechanical philosophy, an orientation within natural philosophy that is associated with nearly every significant early modern philosopher, including Descartes, Boyle, Huygens, Leibniz, and Locke. One of the reasons for this complex relationship can be understood if we consider Newton's attitude towards forces in an abstract way. His second law indicates that a body moving rectilinearly will continue to do so unless the force is impressed on it. This is not equivalent to claiming that a body moving rectilinearly will continue to do so unless another body interacts upon it. A vis impressa, an impressed force in Newton's system, is not the same as a body, nor even a quality of a body, as we have seen. But what is more, some impressed force need not involve contact between bodies at all. For instance, gravity is a kind of centripetal force, and the latter, in turn, in a species of impressed force. Hence, a body moving in a straight line will continue to do so until it experiences a gravitational pull, in which case it will deviate from the straight line of motion, even if no body impacts upon it. Indeed, the gravitational pull might originate with a mass that is millions of miles away. As we have seen, an impressed force is an action exerted on a body. Hence, the gravity exerted on a moving body is an action. The Latin term is actio, which is obviously a causal notion that is not an empirical claim per se. It is merely a reflection of Newton's law together with his notion of an impressed force and his further idea that gravity is one kind of impressed force. These elements of the Principia make conceptual room for causal interaction between two bodies separated by a vast distance, one enabled by Newton's concept of an impressed force. Aspects of this idea became known in philosophical circles as the problem of action at a distance. Many of Newton's most influential contemporaries objected vigorously to the fact that his philosophy had made room for, if not explicitly defended, the possibility of distant action between material bodies. Leibniz and Huygens in particular rejected the aspect of Newton's work in the strongest terms, and it remained a point of contention between Newton and Leibniz for the rest of their lives. Both Leibniz and Huygens were convinced that all natural change occurs throughout contact action, and that any deviation from this basic mechanism principle within natural philosophy would lead to serious difficulties, including the revival of outmoded Aristotelian ideas. But the seventh proposition of Book 3 of the Principia, as we have seen, Newton reached the following conclusion: gravity acts on all bodies universally and is proportional to the quantity of matter in each. Leibniz eventually accused Newton of regarding gravity as a kind of occult quality, that is, as a quality of bodies that is somehow hidden within them and beyond the philosopher's understanding. They understood Newton to be saying that gravity is a kind of hidden power to attract embedded material bodies. Newton was well aware that Principia's methodology of discovering the forces present in nature was controversial, and not merely because of questions about actions at a distance. So when he revised the text under the editorship of Roger Coates for publication in the second edition in 1713, he added other methodological remarks. Those remarks included what Newton called the rules of philosophy, which became the focal point of vigorous discussions and debate well into the 18th century. The first two rules concerned causal reasoning, but it is the third rule that generated the most debate, for it involved an aspect of Newton's controversial argument for universal gravity, and also a rare public statement by Newton of what he regarded as the foundation of natural philosophy. The third rule concerns an induction problem. We have perceptions and experiments that provide us with knowledge of the objects of natural phenomenon in our neck of the universe, but on what basis can we reach a conclusion concerning objects and phenomenon throughout the rest of the universe? Newton himself reached such a conclusion about gravity in Proposition 7 of Book 3 of the Principia. Part of Newton's answer is presented in Rule 3. Those qualities of bodies that cannot be intended and remitted, increased and diminished, and that belong to all bodies on which experiment can be made should be taken as qualities for all bodies universally. We say that a clump of dirt has certain qualities such as extension and mobility, but how do we know that the entire earth has such qualities? It surely lies beyond the reach of our experiments, or at any rate it did in Newton's day. Newton says that the sun and the earth interact according to his law of gravity, but how do we know that the sun contains a quantity of matter, that it has a material body with the same basic qualities that characterize the earth or the moon? It wasn't at all obvious at the time that the sun is a material body at all. Newton thinks that gravity reaches into the very center of the earth, but what did anyone in 1713 know about such things? Newton glossed his third rule in part as follows, connecting it with the laws of motion: that all bodies are movable and preserved in motion or in rest by means of certain forces, which we call force of inertia. We infer from finding these properties in that bodies that we have seen. The extensions, hardness, impenetrability, mobility, and force of inertia of the whole arise from the extension, hardness, impenetrability, mobility, and force of inertia of each of the parts, and thus we conclude that every one of the latest parts of all bodies is extended, hard, impenetrable, movable, endowed with a force of inertia, and this is the foundation of all natural philosophy. Many of Newton's readers in 1713 would have granted him the following inference: although we do not have any perception of, say, the interior of the earth or even many ordinary objects within our grasp, we can reasonably infer that everything with certain basic properties, something akin to what John Locke, borrowing a term of Robert Boyle's, called the primary qualities, at the macroscopic level is comprised of microparticles that are characterized by those same basic properties. But at the end of his gloss of Rule 3, Newton applies the same analogous reasoning to the force of gravity, arguing as follows: since we experience the fact that all bodies on or near the earth gravitate toward the earth in case such as free fall, and that the moon gravitates towards the earth, we can infer that all bodies everywhere gravitate towards all other bodies. This argument would appear to suggest that gravity, which, as we have seen, is a kind of impressed force in action, is somewhat akin to the qualities like extension and impenetrability. So is Newton suggesting that gravity is actually a quality of all bodies? He did not explicitly endorse this claim, but Coates did in the famous passage in his editor's preface. Many understood Coates to be speaking for Newton, just as they interpreted Clarke a few years later. Leibniz and his followers pounced: if Newton regards gravity as a quality, as a power of attraction, then he had indeed revived the occult qualities of the scholastics, for here we have a quality that is not explicable in mechanical terms. Unlike the usual property of extension, impenetrability, and mobility discussed in Coates, gravity seemed like a hidden power This topic became the subject of intense debate throughout the first half of the 18th century. The aftermath of the Principia, relations with John Locke and Richard Bentley. Although the first editions of Newton's Principia and of Locke's essay were published a mere 3 years apart in 1687 and 1690 respectively, their authors worked independently and did not influence the first editions of one another's principal texts. But then in 1688, Locke wrote a sympathetic anonymous review of the Principia, and right around the time of the publication of the first edition of the essay, Newton and Locke became close friends and apparently influenced each other's thinking about philosophy, religion, and theology in various ways. They first met in London in 1689. For his part, Locke called him the incomparable Mr. Newton on several occasions. Most historians think that each questioned the shared Anglican interpretation of the Trinity, contending that Jesus of Nazareth was not a divine figure on the same level as God the Creator, interpreting the Bible through historical and philosophical analysis in a fashion that was not constrained by standard Anglican doctrine in the late 17th century was fantastically important to Newton, occupying his attention for many years. Given their controversial and politically sensitive nature, his so-called anti-Trinitarian views were largely kept secret among a small circle of friends. However, Newton trusted Locke enough to send him a very long letter entitled Two Notable Corruptions of Scripture, to present him with the evidence for Newton's view that the original version of Christianity was corrupted beginning of the 4th century by the introduction of the doctrine of the Trinity. Locke was apparently sympathetic with Newton's approach. With respect to their public view, Newton and Locke were often taken to represent two aspects of the same experimental philosophical approach towards the close of the 17th century. It is perhaps not difficult to understand why, for Newton, was mentioned in one of his most famous passages in all of Locke's writing, in the epistle to the reader of Locke's essay concerning human understanding. Reread, "The commonwealth of learning is not at this time without master builders, whose mighty designs in advancing the sciences will leave lasting monuments to the admiration of posterity. But everyone must not hope to be a Boyle or a Sydenham, and an age that produces such masters in the great Eugenius and the incomparable Mr. Newton, with some other of that strain. 'Tis ambition enough to be employed as an under laborer in cleaning ground a little, and removing some of the rubbish that lies in the way to knowledge, which certainly had been very much more advanced in the world if the endeavors of indigenous and industrious men had not been cumbred with the learned and but frivolous use of uncouth, affected, and unintelligible terms introduced in the sciences, and there made an art of to that degree that philosophy, which is nothing but the true knowledge of things, was thought unfit or incapable to be brought into well-bred company and polite conversation." Clearly, Locke sees in this passage, among other things, to align with his work in the essay with the work of figures like Newton. Here we find at the opening of Locke's magnum opus the suggestion that he is content to be an under-laborer, a thinker who helps to clear the way for the advance of knowledge. But his list of 4 master builders, Boyle, Sydenham, Huygens, and Newton, might strike us as an odd pairing. What do these 4 have in common exactly? It has recently been argued that Locke regarded the 4 as representing the new experimental philosophy, and that Locke himself should be interpreted as strongly supporting that orientation within natural philosophy more generally. This would become a popular conception of Newton's philosophical approach, one that played a substantial role in the Enlightenment. Locke may have regarded Newton as a fellow enthusiast for the experimental philosophy, but there are reasons to think that his embrace of the mechanical philosophy presented him with a difficulty interpreting the consequences of Newton's theory of universal gravity in the Principia. For Newton's theory seemed to be in tension with the mechanist constraint of views of causation, at least from Locke's own point of view. In the first edition of the essay, Locke articulated a central tenet of mechanist thinking about causation when he wrote, "Bodies operate by impulse and nothing else." Impulse here refers to constant contact action. In correspondence with Locke, that would prove to be influential. Bishop Edward Stillingfleet questioned this view from the essay, contending that Locke must jettison the idea of human liberty if he insists that bodies can operate solely by impulse, presumably on the grounds that the human will cannot be understood to cause bodily action in that manner. In a famous exchange, Locke responded in part by reformulating his commitment to a mechanist view that all causation involving material bodies must be by contact impulse alone. It is true, I say, that bodies operate by impulse and nothing else, and so I thought when I read it, and can yet conceive no other way of their operation. But I am since convinced by the judicious Mr. Newton's incomparable book that it's too bold a presumption to limit God's power in this point by my narrow conception. The gravitation of matter towards matter by ways inconceivable to me is not only a demonstration that God can, if he pleases, put into bodies powers and ways of operations above what can be derived from our idea of body, or can be explained by what we know of matter, but also an unquestionable and everywhere visible instance that has done so, and therefore in the next edition of my book I shall take care to have that passage rectified. This was not merely his privately held view. For instance, near the beginning of his Elements of Natural Philosophy, Locke writes, "Two bodies at a distance will put one another into motion by the force of attraction, which is inexplicable by us, though made evident to us by experience, and so to be taken as a principle in natural philosophy." In this way, Locke held the common view that Newton's theory of universal gravity was incompatible with mechanical philosophy, and perhaps unintelligible to us for the very reason. And when forced to choose between these two options, he evidently sided with Newton, thinking that his theory was supported by experience. He did so by endorsing the view that God must have added powers or ways of operations to material bodies that cannot be derived from idea of body. Such powers or ways of operation would in this case result in gravitational interactions, presumably amongst bodies that are spatially separated from one another by great distances. Yet from Locke's point of view, the fact that Newton's theory convinces him that such powers exist does not entail that the theory renders gravity conceivable. Even if the theory of universal gravity is correct, it does not allow us to understand how matter, what Locke would call extended solid substance, can interact gravitationally with other matter when the bits of matter are not in contact with one another. So Locke has concluded that bodies can operate on one another throughout some means other than impulse, but he retains his firmly held belief that any such operation is not intelligible to us. Locke accepted the conclusion that spatially separated bodies causally interact with one another in accordance with the law of universal gravitation, but concluded that the law itself did not render the causal interaction intelligible. This is precisely the kind of reaction to Newton's theory of universal gravity bemoaned by Leibniz, who would argue that any operations or powers attributed to material bodies must meet the basic criterion of intelligibility established by the mechanist approach. He might also be inclined to argue that any law regarded as governing the interactions of bodies must also meet that criterion by being derivable in some way from our basic concept of matter. Regardless, this is an excellent example of a case in which Newton's theory in the Principia had a direct impact on the development of philosophical views of causation in the late 17th century. When the great English natural philosopher Robert Boyle died at the end of 1691, he endowed a lecture series designed to promote Christianity against what Boyle took to be the atheism that infected English culture after the revolutionary period of the mid-century. Famous Newtonians such as Samuel Clarke and William Whiston would eventually give the Boyle lectures. The first Boyle lecture was the theologian Richard Bentley, who would eventually become the master of Newton's alma mater, Trinity College, Cambridge, and who also worked under Locke's correspondent Bishop Stillingfleet, himself an admirer of Newton. When preparing his lectures for publication, they'd been presented to a public audience in London in 1692. Bentley conferred with Newton, hoping to solicit his help in deciphering enough of the Principia to use its results as a bulwark against atheism. Newton obliged, and a famous correspondence between the two began, eventually published as Bentley 1756. The exchange is of great philosophical interest, for Bentley elicited a number of important clarifications that have no peer within Newton's published oeuvre. Bentley sought Newton's assistance in particular because he wanted guidance in divining how the theory of the Principia indicates that the solar system must have been designed by an intelligent agent and could not have arisen throughout the physical interactions of material bodies. In the first edition of the Principia in 1687, Newton had made such a claim in a very brief statement. In the second edition of the text published in 1713, he removed that statement, replacing it with more extensive discussion in the new section of the text added to its end called the General Scholium. Though through their correspondence, Bentley learned that Newton's point of view, the position of the planets relative to one another, and especially the sun, indicate that mere chance or the ordinary physical interactions of planetary bodies could not have placed each planet precisely the right orbit to maintain the solar system like ours for an extended period of time. With this argument, Newton seems to be indicating that mere chance would have produced an unstable planetary system, one in which the planets would eventually either be too strongly attracted to the sun, falling into it, or too weakly attracted, flying off into space. In this episode, the theologian appealed appeals to the new authority of Newtonian natural philosophy when attempting to undermine atheism. And that was apparently the very first kind of exchange that Boyle had envisioned when endowing the lecture series. Newton's correspondence with Bentley is justly famous for another reason. The criticisms of Newton's theory of gravity by Leipzig and Huygens, outlined briefly above, would prove essential to the continental reception of Newtonian natural philosophy more generally in the late 17th and early 18th century. Since Newton held both of these mathematicians in high regard, he tells Leibniz in a 1693 letter that Huygens is a master and his remarks on my discoveries are brilliant. One might assume that their criticisms would have pressed Newton into articulating an extensive defense of the possibility of action at a distance. However, Newton presented no such defense, at least not explicitly. In fact, there is evidence that Newton himself may have rejected the possibility of action at a distance, despite the fact that the Principia allows it as conceptual possibility, if not an empirical reality. The evidence lies in Newton's correspondence with Bentley in February of 1693 after receiving 3 letters from Newton. Bentley wrote an extensive reply that attempts to characterize Newton's theory of gravity, along with his understanding of the nature of matter, in a way that could be used to undermine various kinds of atheism. With 3 earlier letters as his guide, Bentley makes the following estimation of Newton's understanding of the possibility that gravity could somehow be an essential feature of material bodies. And as for gravitation, 'tis impossible that should either be co-eternal and essential to matter, or even acquired by it, not essential and co-eternal to matter, for then even our systems would have been eternal if gravity could form them. Against our atheist supposition, and what we have proved in our last, for let them assign any given time that matter convened from chaos into our system. So they affirm that before the given time matter gravitated eternally without convening, which is absurd. So I make account that your courteous suggestion by your last that a chaos is inconsistent with the hypothesis of innate gravity is included in the paragraph of mine. And again, 'tis inconceivable that innate brute matter should, without a divine impression, operate upon and affect other matter without mutual contact, as it must if gravitation be essential and inherent in it. In reply to this letter, Newton refers back to the second proposition, making one of the most famous of all his pronouncements concerning the possibility of action at a distance. Hey, Malthus, God bless. The last clause of the second proposition I like very well. It is inconceivable that inanimate brute matter should, without the mediation of something else which is not material, operate upon and affect other matter without mutual contact, as it must be, if gravitation in the sense of Epicurus be essential and inherent in it. And this is one reason why I desired you would not ascribe innate gravity to me. The gravity should be innate, inherent, and essential to matter, so that one body may act upon another at a distance through a vacuum without the mediation of anything else, by and through which their action and gravity may be convened from one to another, is to me a great absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into. Gravity must be caused by an agent acting constantly according to certain laws, but whether this agent be material or immaterial, I have left open to the consideration of my readers. It certainly seems that Newton was uncomfortable with the very idea of action at a distance, but of course things are not always as they seem. In interpretations of difficult philosophical texts, some historians and philosophers have argued strongly that there are other readings of the letter. Rather than rejecting distant action between material bodies per se, they argue Newton may have been rejecting a particular version of the idea, one associated with the Epicurean view that gravity is somehow an essential feature of all material bodies, a stronger view than Newton might wish to endorse. The idea might be roughly as follows. Newton wanted to leave open the possibility that God had endowed bodies with the power to act at a distance on one another, a position that is least reminiscent of Locke's view in his correspondence with Stillingfleet. The reason is that Newton held that standard view at the time that matter itself is passive, requiring some kind of divine intervention in order to interact causally with other matter. Again, one finds a Lockean echo of this idea, which may be no accident. Locke sometimes suggests that matter itself is passive in the sense that it cannot move itself. Instead, motion must be superadded to it by God. If the world consisted solely of a bunch of material objects, say rocks floating in interstellar space, then they would not experience any changes in their states of motion unless some external force acted upon them. Left to their own devices, matter is passive and does not move. To argue, as some Epicurean philosophers may have done, that matter itself essentially contains gravity as a feature is to deny that matter is passive. It is suggest that the rocks in interstellar space would attract one another and begin to move on their own without any external force influencing them. And this, in turn, might lead us on a slippery slope to atheism, for on this view, matter would act on its own without any divine intervention, or so Bentley and Newton might be interpreted. Clearly, one reasonable motive for undercovering a nuanced interpretation of Newton's letter to Bentley is the obvious fact that Newton apparently regarded action at distance as perfectly possible when writing the Principia. Indeed, it is difficult to reconcile the Principia with the Bentley correspondence. One can argue that although he left open the possibility of action at distance in his main work, Newton himself did not accept that possibility because of his more general commitments. The debate on such matters continued unabated. However, regardless of Newton's personal attitudes towards distant action among material bodies, his mechanist interlocutors and readers continued to object to the physical theory outlined in Book 3 of the Principia on the grounds that, at the very least, it left open the conceptual possibility of a kind of action that cannot, in fact, exist anywhere in nature. That remained one of Leibniz's principal objections against Newtonian natural philosophy throughout the last 20 years of his life, animating his correspondence with numerous figures, including most prominently the Newton theologian and philosopher Samuel Clarke. Let's get another drink. The aftermath of the Principia debates with Leibniz. In many ways, Leibniz and Newton grew up in the same philosophical environment. Each came of age during the heyday of Cartesianism, and each argued in particular that Cartesian views in natural philosophy failed to include a sufficiently robust conception of the forces of bodies in nature. Force would lie at the center of Newton's mature physics, and would become even more central to Leibniz's thinking, playing a central role in his metaphysics as well. Indeed, in Leibniz's criticisms of Cartesian physics involving what was later called the vis viva controversy, and in Newton's mature physics, each argued that Descartes and his followers had failed to understand the importance of the notion of force. Leibniz and Newton knew one another as mathematicians already in the 1670s, and it's been seen Leibniz discovered Newton's first optical work with Huygens. But after the publication of the Principia in 1687, their philosophical relationship, which was marked originally by respectful disagreement, began to develop in earnest. Just 2 years after the Principia appeared, Leibniz published his essay on the causes of celestial motions, or Tentamen, and then in 1693, the two corresponded with one another on mathematical and philosophical issues. Okay, Elemental, God bless. Leibniz initiated their discussion in March of 1693 after highlighting Newton's astonishing discovery that the elliptical planetary orbits found in Kepler can be the result of gravitational attraction within the solar system. Leibniz contends that these motions must be caused by the motion of a fluid medium. He had described such fluid medium or vortex in detail in his own essay. The background to Leibniz's comment is his unwavering commitment, one shared by Huygens, whose theory of gravity caused Leibniz mentioned in the same letter to be the mechanist requirements that all changes in motion must be the result of a material impact. Thus, for Leibniz, one can speak of the sun as attracting the earth as a facunda parlor, but in fact, the cause of the earth's acceleration of its true motion around the sun is an interaction with fluid mediums. Descartes is also a famous proponent of the vortex theory of planetary motion. When he replied in October of 1693, however, Newton did not accept Leibniz's philosophical olive branch. Leibniz had insisted that the vortex theory of planetary motion would not at all detract from the value and truth of your discovery, that Kepler's ellipse results simply from this conception of attraction or gravitation. This olive branch was important because earlier vortex theorists, especially Descartes, had failed to account for Kepler's laws, so Leibniz was crediting Newton with advancing astronomy in this respect, and indeed attempted to reflect Kepler's results in his Tentamen. But Newton brushed aside the olive branch, noting that vortices would disturb the motion of the planets and comets through the solar system. He writes that some very fine matter fills the heavens, adding, "For since celestial motions are more regular than if they arose from vortices and observe other laws, so much so that vortices contribute not to the regulation, but to the disturbance of the motion of planets and comets. And since all phenomena of the heavens and the sea follow precisely, so far as I'm aware, from nothing but gravity acting in accordance with the laws described by me, and since nature is very simple, I myself included that all other causes are to be rejected, and that the heavens are to be stripped as far as may be of all matter, lest the motions of planets and comets be hindered or rendered irregular. But if meanwhile someone explains gravity along with all its laws by the action of some subtle matter, and shows that the motion of planets and comets will not lie disturbed by this matter, I shall be far from objecting. This passage, rich with meaning, Leibniz clearly insisted that vortices or some physical object or fluid must be in contact with the planetary orbit if we are to explain why they deviate from the tangents along the orbital paths when circulating the sun. Newton's reply is that giant swirling fluids in the heaven would actually disturb the regular orbital paths and the paths of the comets through the solar system. That reply might be thought of as empirical in character, for it depends on observational data regarding the actual paths of the heavenly bodies. But Leibniz's perspective is obviously not merely empirical in character. He does not postulate vortices or anything akin to them on observational grounds. He infers their existence because he thinks we know. Perhaps we can add, we know a priori that physical bodies such as comets and planets cannot deviate from the rectilinear path. They can accelerate only if some other physical item impacts upon them. Newton had a reply to the kind of view as well. He insists that the phenomenon of the motion of the heavenly bodies follows solely from gravity itself, an impressed force, as we have seen, and therefore an action in accordance with the laws of motion of the law of universal gravitation. Since gravity is an action, clearly a causal notion, it seems clear that Newton's answer to Leibniz's idea that vortices cause the planetary orbits is that gravity itself causes them. It is not much of a leap to conclude that in turn that this reply commits Newton to the idea that bodies involved in gravitational interactions, such as the sun and the earth, act at a distance on one another through the force of gravity. It is not hard to divine why Leibniz and Huygens would have concluded that Newton had relinquished any commitment to the norms of mechanical philosophy. Despite Leibniz and Huygens' criticisms of his theory of gravity in particular and his methods in natural philosophy in general, Newton stuck to his guns. Nearly 20 years after their illuminating exchange in 1693, Leibniz and Newton narrowly missed a second opportunity to discuss their philosophical differences directly. In May of 1712, Leibniz published a letter to Nicholas Hartsaker that was highly critical of Newtonians. It was published in English translation in Memoirs of Literature, a journal which Robert Coates, the editor of Principia's second edition, held a subscription. After Coates brought Leibniz's criticisms to Newton's attention, especially the claim that Principia renders gravitation a perpetual miracle because it does not specify the physical mechanism underlying it, Newton wrote an intriguing but only pusillanimously published rebuttal. Here is part of Newton's paraphrase of Leibniz's original letter. But Leibniz goes on and tells us that God could not create planets that should move round of themselves without any cause that should prevent their removing through the tangent. For a miracle, at least must keep the planet in. Newton's response to the Leibnizian charge is illuminating, but certainly God could create planets that should move around of themselves without any other cause than gravity that should prevent their removing through the tangent. The gravity without a miracle may keep the planets in. Thus, Newton repeats his view he mentions to Leibniz in 1693 that the force of gravity itself causes the planets to follow their orbital paths rather than their inertial trajectories along the tangents to those orbits, independently of any fluid medium in the heavens. But in this pusillanimously published letter, Newton did not merely repeat his basic understanding of gravity from his 1693 exchange with Leibniz, he also included a wider discussion of mechanist norms within philosophy more generally. Again, Newton begins by quoting Leibniz. But Mr. Leibniz goes on, the ancients and the moderns who own that gravity is an occult quality are in the right if they mean by it that there is a certain mechanism unknown to them whereby all bodies tend towards the center of the earth. But if they mean that the thing is performed without any mechanism by a simple primitive quality or by a law of God who produces that effect without using any intelligible means, it is unreasonable and occult quality, and so very occult that it is impossible that it should ever be done through an angel or God himself should undertake to explain it. In this passage, Leibniz returns to the kind of criticism that he would present against the superaddition view that Locke presented to Stillingfleet, arguing that philosophers must reject the idea that gravity could simply be a feature of bodies that God adds to them, despite the fact that we cannot possibly understand gravitational interaction based on our idea of body, our idea of extended solid substances, or another similar idea. Indeed, Leibniz raises the stakes by contending that God himself could not explicate how such interactions are possible based on the idea of matter. Leibniz would argue, perhaps on metaphysical grounds, that any law said to govern the interaction of bodies and any quality attributed to bodies must be intelligible in terms available to philosophers through the mechanist orientation. In particular, laws and qualities must be intelligible in terms of the shape, size, motion, and impenetrability or solidity of bodies. In this way, one might conclude that Locke and Leibniz actually do not necessarily disagree on whether gravity can be made intelligible in mechanistic terms. They simply disagree on the properties of the contention that God could superadd a feature to bodies that cannot be made intelligible in that way. Newton's reply to Leibniz's argument is illuminating. Instead of presenting a narrow defense of this view, perhaps by denying that he postulated any non-mechanical causation with his theory of gravity, he challenges the mechanical philosophy itself by contending that it should not be understood as holding for all natural phenomena. The same ought to be said of hardness, so then gravity and hardness must go for unreasonable occult qualities unless they can be explained mechanically, and why may not the same be said of the vis inertiae, force of inertia, and the extension, the duration, and mobility of the bodies, and yet no man ever attempted to explain these qualities mechanically or took them for miracles or supernatural things or fictions or occult qualities. They are the natural, real, reasonable, manifest qualities of all bodies, seated in them by the will of God from the beginning of the creation and perfectly incapable of being explained mechanically, and so may be the hardness of primitive particles of bodies. And therefore, if any man should say that bodies attract one another by a power whose cause is unknown to us, or by a power seated in the frame of nature by the will of God, or by a power seated in substance in which bodies move and float without resistance, and which has therefore no vis inertia, but acts by other laws than those that are mechanical, I know not why he should be said to introduce miracles and occult qualities and fictions in the world, for Mr. Leibniz himself will scarce say that thinking is mechanical, and it must be, if to explain it otherwise, be to make a miracle, an occult quality, and a fiction. The first aspect of Newton's argument is to indicate that mechanical explanations are predicated on referencing certain kinds of qualities when investigating natural phenomena, and that these qualities themselves are therefore not subject to mechanical explanations. For instance, since mechanist explanations say on the way in which magnets attract iron fillings across a table must refer to the qualities such as the extension of the body subject to the explanation, then we cannot give a mechanist explanation of the extension itself. Of course, Leibniz might reply that we need not provide any explanation of the basic qualities of bodies that figure in mechanical explanation, for those properties have been chosen by the moderns precisely because they are perfectly intelligible on their own, perhaps unlike various qualities attributed to scholastic accounts of natural phenomena. The second aspect of Newton's argument is more intriguing. It also harkens back to Locke's discussion with Stillingfleet, for Locke had contended that God may have superadded not only gravity to material bodies, but also the power of thought, linking them because he believes that neither could be rendered intelligible using any philosophical means at his disposal. That is, from Locke's point of view, we know that human beings, which are at least contain material bodies with size, shape, motion, and solidity, along with parts characterized by those qualities, are capable of thought. But since we cannot discern how many material things could possibly have that capacity, we conclude that God may have superadded that feature to us and to our bodies. Thought and gravity are disanalogous in the sense that we did not require anything like Newton's theory to convince us that human beings can think, but they are otherwise analogous. Newton then attempts to make the following argument. Since Leibniz would have to agree that thinking is not a mechanical process and not mechanically explicable, he must agree that there is at least one aspect of the world that has the following two features. One, it is not mechanical, and two, it is clearly not to be rejected on the grounds alone. He attempted to liken gravity as he understands it to thinking, as he believes Leibniz is required to understand it, arguing that despite the fact that it is not mechanical, it cannot be explained mechanically. It should not be rejected on that ground. This argument may be predicated on the view that human beings, material things, or at least partially material things, do the thinking, rather than immaterial things such as minds or souls. For if one attributes all thoughts to an immaterial mind or soul, then there's no pressure to say that anything in nature, or perhaps even any aspect of anything in nature, has a feature that cannot be mechanically explicated. If one accepts Locke's views, apparently also endorsed by Newton, that we should attribute thinking to material things or to aspects of material things, then perhaps Newton has successfully followed Locke in likening gravity to thought. thereby making room for aspects of nature that are not mechanical after all. This vexing issue would continue to generate debates among Newton and Leibniz's various followers in England and on the continent, respectively. Leibniz's most extensive debate with the Newtonians would not occur until the very end of his life. His celebrated correspondence with Samuel Clarke, Newton's friend and supporter in London, in the early part of the 18th century, is his most famous interaction with the Newtonians, occurring right before his death in 1716. Leibniz fomented the correspondence in November 1715 by sending a brief, provocative letter to Princess Caroline of Wales, one designed to provoke a response from Newton's circle in London. Leibniz knew well that Princess Caroline was a leading intellectual and political figure in England at the time, one who would surely be concerned by Leibniz's shocking claims about the religious consequences of Newtonian thinking. He opens an initial letter by mentioning both Locke and Newton, along with the issue about materiality and thinking that arose in his near exchange with Newton in 1712. Natural religion itself seems to decay in England very much. Many will have human souls to be material, others make God himself a corporeal being. Mr. Locke and his followers are uncertain at least whether the soul is not material and naturally perishable. Sir Isaac Newton says that space is an organ which God makes use of to perceive things by, but if God stands in need of any organ to perceive things by, it will follow that they do not depend altogether on him, nor were produced by him. Thus, Leibniz charges both Lockeans and Newtonians with presenting philosophical views of the human and the divine that lead to theologically unsavory consequences, such as the idea that the human soul might be material, and the view that God must employ something akin to an organ in order to perceive happenings in the world. These were fighting words. Although Locke had died in 1704, he had various followers in England at the time, and Newton himself was at the height of his influence. He had by then been knighted, as Leibniz acknowledges by calling him Sir in his letter, and was at the time president of the Royal Society. Moreover, Samuel Clarke had given the Boyle Lecture in 1704 and again in 1705, so he was a public figure associated with the state of Christianity in England. Once Clarke took the bait, replying the same month to Leibniz's charges, Locke's views quickly dropped from the view, and the two focused specifically on Leibniz's numerous objections to the Newtonian ideas and methods. But why did Clarke respond on Newton's behalf, and what was Newton's actual role in the correspondence? These questions continue to puzzle scholars. There's no documentary evidence, such as letters between Clarke and Newton, indicating the contours of his role. Then again, at the time, both men lived in London, and Clarke was Newton's parish priest, so the lack of letters or other papers is perhaps unsurprising. That fact alone is intriguing, for the theological differences between the two are salient, since Newton was a committed anti-Trinitarian, a fact known to figures like Locke and to others such as William Whiston. He may have decided that Leibniz's contention about natural religion in England would best be answered by what we might now call a more mainstream theological figure like Clarke. In any event, there is no doubt that Clarke was taken by Leibniz and his followers to be speaking for Newton and his circle. Nonetheless, there are certain aspects of Clarke's view that may deviate from Newton's own opinion. So it would be unwise to, as it were, remove Clarke from our conception of the correspondence by regarding it as effectively as Newton's work. Leibniz's side of the correspondence with Clarke is methodologically characteristic. He leaves much of his own systematic and complex metaphysical theorizing, including monadology, in the background, bringing to the fore only those elements that are both necessary for his criticisms of the Newtonians and also likely to garner support from Clarke. Thus, the key to many of Leibniz's criticisms and the principle of sufficient reason, which he knows Clarke will endorse, although with a distinct conception of its scope. Leibniz asserts, while Clarke denies, that the principle demands that each of the divine willing requires a reason. For Clarke, divine willing itself is a reason enough for some physical state of affairs to obtain or event to occur. Leibniz argues in particular that several key aspects of the Newtonian worldview are simply incompatible with the principle of sufficient reason, including the idea of absolute space. If space were, in fact, completely independent of all physical objects and in relation among them, as the Newtonian seems to assert, then a problem arises. I have many demonstrations to confute the fancy of those who take space to be a substance or at least an absolute being, but I shall only use at present one demonstration which the author here gives me an occasion to insist upon. I say then that if space were an absolute being, something would happen for which it would be impossible that there should be a sufficient reason, which is against my axioms, and I prove it thus: space is something absolutely uniform, and without the things placed in it, one point of space absolutely does not differ in any respect whatsoever from another point of space. Now, from this, it follows suppose space is to be something in itself besides the order of bodies among themselves. That is impossible. There should be a reason why God, perceiving the same situation of bodies amongst themselves, should have placed them in space after one certain particular manner and not otherwise. Why everything was not placed the quite the contrary way, for instance, by changing east into west. But if space is nothing else but this order of relation, and is nothing at all without bodies but the possibility of placing them, then those two states, the one such as it is now, and the other supposed to be quite contrary way, would not at all differ from one another. Their difference, therefore, is only to be found in our chimerical superstition of the reality of space. Leibniz's argument is a clever at the outset. He bypasses the thorny problem of determining whether Newton's idea of absolute space commits him to thinking of space as a substance, a view, incidentally, which Newton explicitly considers and rejects in De Gravitatione by presupposing only that Newton thinks of space as existing independently of objects and their relations. If space is indeed independent in this way, then it would seem that God faces a choice when creating the world or matter. Why place the Earth in one particular part of space rather than any other? The parts of space independently of all objects and all relations obviously do not differ from one another in any respect at all. So it would seem that one could not even theoretically devise a reason for placing the Earth anywhere in particular as opposed to anywhere else. This argument, incidentally, does not depend on our having the capacity to refer the two places within empty space. But since space exists with all of its places independently of the Earth and everything else, then God must indeed have some reason to place the Earth in one particular one place rather than another. For Leibniz, even the divine will is inert, independent of any reason for, as it were, moving in one direction rather than another. Finally, Leibniz argues that he himself avoids this problem by asserting that space is nothing above and beyond the objects in the world in all possible relations among them. Hence, he holds a kind of modal relationalist view. In more modern terminology, God faces no problematic choice of this view, since space does not exist prior to the creation of the world or of material objects. To create objects with spatial relations is ipso facto to create space itself, for it is nothing over and above objects and their relations. If you like, a space for Leibniz just as a way of conceptually grasping all objects and all possible relations among them all at once. Time, similarly, is a way of grasping the whole series of events that have characterized history. Clarke's reply is somewhat disappointing. He blocks Leibniz's inference by simply denying that the divine will must have a reason to place, say, the Earth in one place rather than another. The principle of sufficient reason is not violated in this case, according to Clarke's interpretation of it, because it requires only this: if the Earth appears in one place rather than another, there must be a reason that it appears there, and the reason in this case is simply the divine will. There's no further question about why the divine being made a particular choice rather than another. In the quotation above, Leibniz speaks of the Newtonians as endorsing the reality of space, which Leibniz regards as chimerical. This remark highlights another important aspect of Leibniz's conception of space and time, one that is often ignored in contemporary discussions, which tends to emphasize the Leibnizian relationalism in opposition to Newton's absolutism. Leibniz's view of space and time connects intimately with broader aspects of his metaphysical positions. Unlike ordinary physical objects, which are constituted by their parts, they are discrete, and which exhibit features that involve internal distinctions amongst those parts. He thinks of space and time as continuous and homogeneous, leaving aside the mononology, as he does in his correspondence with Clarke. This means that for Leibniz, it is physical objects that are real things. Space and time are merely ideal or abstract entities whose continuity and homogeneity signal this special status. It is not merely that space and time are nothing over and above the events and relations of objects that exist in our world. It is also the case that they are ideal. They depend on, in some way, on the human mind for their existence, or so Leibniz seems to suggest. This aspect of his view would become of central importance to later Kant's conception of the Leibniz-Newton debate on the nature of space. Obviously, Leibniz's arguments against the Newtonians highlighted a fundamental difference between his interpretation of the principle of sufficient reason and Clarke's, where Leibniz held that what we might call the rationalist view, that all willing, all choice must occur for a reason, a requirement from which the divine being is not exempt. Clarke held what we might call the voluntarist view, that willing or choice itself need not occur for any reason, for it is self-sufficient reason for some states of affairs to obtain or event to occur. For Leibniz's point of view, this renders the will, including the divine will, opaque or intelligible. If an agent can act or make a choice without having any reason for it, then surely the agent is not rational. And if the principle of sufficient reason demands anything in this world, it is that the world be rationally intelligible to us. This requirement must hold of agents and their wills as well. But from Clarke's point of view, this requirement is too stringent, especially in the divine case. If we hold that even God must have a reason for choosing to create one state of affairs rather than another, for choosing, say, to part the Red Sea rather than the Mississippi River, then we are ipso facto restricting God's freedom. Surely God has the freedom to choose to do something, anything at all, or at least anything that does not contain or instantiate a contradiction. And for his part, Leibniz agrees that the principle of contradiction does not entail the principle of sufficient reason. The latter is separate and independent principle, which is necessarily for metaphysics and natural philosophy to extend beyond mathematics, which requires only the principle of contradiction. But he thinks that Clarke's view leaves us with a God, and indeed with ordinary agents who can act arbitrarily with no reason at all. That is not the kind of freedom that philosophy seeks. It wishes to see agents as engaged in rational action and their differing interpretations of the principle of sufficient reason, and their correspondingly distinct conceptions of freedom and reason. The debate between Leibniz and Clarke hits rock bottom. Leibniz's criticism of the Newtonians were not restricted to the question about the nature of space and time. He also revived his old complaint, one shared by Huygens, as we have seen above, that Newton's physical theory commits him to the possibility, if not to the reality, of action at a distance among the planetary bodies. In one passage in his fourth letter, for instance, Leibniz writes, "It is also a supernatural thing that bodies should attract one another at a distance without any intermediate means, and that a body should move around without receding in the tangent, though nothing hinders it from so receding, for these effects cannot be explained by the nature of things." As a defender of the mechanical philosophy, Leibniz insists here, as he had before, that a material body like that Earth would recede along the tangent to its orbit if it were not impacted upon some physical body or bodies, such as a vortex or another kind of fluid filling the solar system. Clarke replies, to this charge is especially illuminating. That one body should attract another without any intermediate means is indeed not a miracle, but a contradiction, for 'tis supposing something to act where it is not. But the means by which two bodies attract each other may be invisible and intangible, and of a different nature from mechanism, and yet acting regularly and constantly may well be called natural, being much less wonderful than animal motion, which yet is never called a miracle. This passage is bound to confuse readers. On the one hand, Clarke is clearly arguing that Newtonians refuse to restrict their understanding of causal interactions in nature to mechanical cases. On the other, however, he does accept what many in the time would have regarded as the obvious implication of the denial of mechanism, namely that action at a distance is perfectly possible, a move embraced by some later in the 18th century, such as Kant. Indeed, Clarke not only rejects action at a distance, as Newton possibly had before him, he contends that it isn't even logically possible. In his various pronouncements to Bentley and others, Newton never contended that action at a distance was simply a contradiction and therefore impossible. Presumably, even for the divine being, who is typically said to be capable of creating any situation, does not instantiate a contradiction, although Descartes' views on the eternal truths are obviously more complicated. Clarke's view raises serious problems for the Newtonians. If action at a distance is simply a contradiction and therefore not a possible physical situation, even with divine intervention, then how should one interpret the theory of universal gravity, which certainly appears to indicate that distant action is perfectly possible and perhaps even actual? If we interpreted the theory as postulating actual distant action, say between the moon and the earth, then it clearly must be mistaken. But even if we interpret it less strongly as merely postulating that distant action between the moon and the earth is possible, that would presumably disqualify the theory as well. Perhaps one can save Clarke's view by contending that since distant action is logically impossible, Newton's theory must therefore be interpreted as neutral on that issue. This is one issue where Clarke's views may differ substantially from Newton's own. Regardless of whether Clarke represented Newton's own views faithfully, there is no doubt that his correspondence with Leibniz helped to shape the agenda of philosophy in the 18th century. And finally, Newton's impact on philosophy. The history of the 18th century philosophy cannot be written without extensive discussion of Newton's own view and his influence on the views of other figures in both England and the continent. As we have seen when Newton was a young student at Trinity College, Cambridge, Cartesian views in natural philosophy and much else besides had replaced the ideas and methods of Aristotle and his followers as most important subject for discussion among philosophers. In many ways, Newton eventually succeeded in convincing philosophers that his own ideas and methods were superior to those of the Cartesians, especially when it came to thinking about motion and its causes. But this historical fact did not mean that Newtonianism, even broadly construed, became the dominant trend in natural philosophy during Newton's lifetime. On the contrary, Newton's views continued to be the subject of intense scrutiny and debate. As we have seen, this was true among Leibniz and his followers, such as Christian Wolff, and among fellow mechanists such as Huygens. Indeed, a late 17th century debate between Cartesian and Newtonian ideas was supplemented by an early 18th century debate between Leibnizian and Newtonian views. The latter debate would continue in one form and another for the rest of the century. But even amongst leading continental mathematicians, some of Newton's most basic ideas, for instance, concerning the forces of nature, remained the subject of dispute until well into the 18th century. To give just one prominent example that influenced the development of philosophy, D'Alembert and Euler, two of the greatest mathematicians of the Enlightenment, had opposite reactions to Newton's ideas that the mass of an object could also be referred to by the very significant name of the vis inertia, or of the force of inertia. These discussions, along with numerous other debates about space-time and motion, were a driving force during the French Enlightenment. They remained a powerful stimulant to philosophical theorizing in the 1770s and 80s when Kant forged his magisterial critical system of philosophy, an approach that almost single-handedly set the philosophical agenda of the early 19th century. Hence, Newton's influence on the 18th century did not take the form of a single philosophical program or movement. Instead, it was the controversial nature of his ideas and methodology that drove much of the philosophical discussion. Newton's ideas and method were certainly most influential in Britain, where they grew to be a strong Newtonian movement, also called the experimental philosophy program, by roughly 1700. By the fin de siècle, it is probably safe to say that natural philosophy had become heavily Newtonian in England, at least in the sense that it eclipsed both Cartesianism and other local movements such as Cambridge Platonism, which had exhibited a strong influence during the previous generation. One might put the point somewhat differently to the extent that there was a dominant strand in England by 1700. It was the experimental philosophy of view that was associated strongly with figures such as Boyle, Newton, and Locke. Figures such as Hobbes had opposed this approach to solving philosophical problems, but it failed to gain nearly as much influence. Perhaps more importantly, Newton's view of motion, his understanding of space and time, and his approach to achieving knowledge of natural phenomenon helped to shape the agenda of British philosophy for the next 50 years. In addition to Newton's influence on Locke and thinking about matter and causation, explored above both Berkeley and Hume, expended considerable energy grappling with the wider consequences and implications of the Newtonian version of the experimental philosophy. For his part, Berkeley famously derided many Newtonians' method and ideas, sometimes exempting Newton himself from his conception of the worst philosophical excesses of his followers, including the rise of the calculus among mathematicians and the analysts, and the use of the idea of force as the basic causal concept in natural philosophy into Newton. Berkeley's theory of ideas, which arose in part from his reflections on what we would now call Locke's empiricist notion of representation, suggested him that no idea can be abstract. Each idea must represent a particular rather than a universal. Hence, we can have an idea of a particular car, say a yellow two-door sports car, but not of a car in general, one with no specific characteristics. Similarly, we can have an idea of a particular shade of yellow, perhaps because we've just seen a lovely yellow rose at the florist, but not of yellow in general, and so on. Berkeley then argued that modern mathematics, especially the calculus and modern natural philosophy, especially the Newtonian version of it, were often reliant on abstract ideas and therefore philosophically suspect. For instance, he contended that the very idea of absolute motion was suspect because we can represent to ourselves only various motions with particular features related to particular bodies in motion, but absolute motion cannot be rendered particular in anything like this way. It remains abstract. Thus, although Newtonian views were considered to be essential to the rise of experimental philosophy in Britain, Berkeley derided them as insufficiently experimental or empirical, as overtly reliant on representations of universals and of universal quantities, rather than on representations of particulars. And in reflection of Mellenbrook's influence, Berkeley also argued that some Newtonians wrongly attributed genuine causal powers to ordinary material objects through their use of the concept of impressed force, wrongly because Berkeley firmly rejected the notion that any body could exert any causal power. All causation in Berkeley's system is due either to the intervention of the divine in the course of history, or to spirits or minds which are genuinely causally active. Finally, an argument that would prefigure Mach's reaction to Newtonian concepts of space-time and motion in the late 19th century, which were expressive of a broad commitment to empiricism. Berkeley contended that absolute space is metaphysical aberration. Philosophers should not posit any entity or thing that is beyond all possible perception. In sum, Berkeley was highly critical of many aspects of the Newtonian program, but for that very reason, it was Newton's ideas that helped to shape many of the philosophical projects. For his part, Hume had a more nuanced reaction to the emergence of the Newtonian program. He certainly signaled his endorsement of the experimental philosophy, itself strongly associated with the Newtonians, along with figures like Boyle and Hooke, as we have seen when he gave his treatise the following subtitle, being an attempt to introduce the experimental method of reasoning into moral subjects. And one might argue that Hume made a kind of Lockean move when he chose to endorse the Newtonian program, specifically in preference to the mechanical philosophy, which he regarded with suspicion. A famous comment from his History of England bolsters this interpretation. While Newton seemed to draw off the veil from some of the mysteries of nature, he showed at the same time the imperfections of the mechanical philosophy, and therefore restored her ultimate secrets to the obscurity in which they ever did and ever will remain. The difference between Locke and Hume might be that the former, unlike the latter, nonetheless insisted that mechanism continued to provide philosophers with a canon for the intelligibility of causation within nature. Hume's critique of earlier conceptions of causation, including Locke's, is certainly well known. Hume also expended considerable effort in interpreting some of the philosophical aspects or consequences of Newton's theory of gravity and his corresponding understanding of the nature of matter. In particular, he wished to provide what we would now call an empiricist interpretation of Newton's three laws of motion, his concept of mass, quantity of matter, and his understanding of gravity. In the process, he does not shy away from interpreting Newton's sometimes confusing notion of the vis inertiae, or force of inertia. When students learned the canonical idea of a Newtonian force, they learned about what Newton called the vis impressa, or impressed force. They also learned that the mass of a body is not a force at all, but in all three editions of the Principia, Newton himself said that although the mass of a body is not an impressed force, it could be called the very significant name of force of inertia, because bodies with mass resist acceleration, and to resist acceleration seemed to Newton like an action that a body performs, say when the other body collides with it. Now for Hume, this issue was particularly difficult because he had already contended that, strictly speaking, we have no idea, no representation of a force or power. These are merely words employed by natural philosophers without any ideas corresponding to them. Thus, he might find an interpretation of Newton that is not predicated on our ability to form an idea of forces or powers. In a famous footnote in his inquiry concerning human understanding, Hume writes, "I need not examine at length the vis inertia, which is so much talked of in this new philosophy, and which is ascribed to matter. We find by experience that a body at rest or in motion continues forever in this present state, till put from it by some new cause, and that a body impelled takes as much motion from the impelling body as it acquires itself. These are facts. When we call this a vis inertia, we only mark these facts without pretending to have any idea of that inert power, in the same manner as when we talk of gravity, we mean certain effects without comprehending that active power. It was never the meaning of Sir Isaac Newton to rob second causes of all force or energy, though some of his followers have endeavored to establish that theory upon his authority. On the contrary, that great philosopher had recourse to an internal active fluid to explain his universal attraction, though he was so cautious and modest as to allow that it was a mere hypothesis, not to be insisted on without more experiments. In mentioning Newton's speculation that ether might explain universal gravity in some sense, Hume does not appear to be concerned about action at a distance. Instead, he is concerned to argue that this speculation indicates that Newton himself did not regard his theory as requiring that we attribute a power of gravity to material bodies. This is important for Hume to establish, not least because he believes that we can form no representation at all of any such power. Similarly, when Newton indicates in the Principia that we can conceive of a body's quantity of matter as its vis inertia, its power of resisting any change to its state of motion, he is not attributing any power to that body, but rather employing a means of characterizing its behavior, or so Hume contends. In this specific regard, we find an echo of Berkeley's earlier work in De Muto. Berkeley argues in particular that although some philosophers misunderstood the Newtonian theory of gravity as attributing a special force of nature to material objects, there is an interpretation of Newton that is consistent with the new theory of ideas. He writes again, force, gravity, and terms of that sort are more often used in the concrete, and rightly so, as to connote the body in motion, the effort of resisting, but when they are used by philosophers to signify certain natures carved out and abstracted from all these things, natures which are not objects of a sense, nor can be grasped by any force of intellect, nor pictured by the imagination, then indeed they are breed errors and confusion. There's little doubt then that the new British philosophy represented by Locke, Berkeley, and Hume in the early to mid 18th century was concerned to present interpretations of Newton's work that were consistent with their overarching philosophical commitments, principles, and methods, or to alter those commitments, principles, and methods as necessary. These attempts by canonical philosophers like Berkeley and Hume to find what they regarded as a defensible interpretation of Newtonian forces are mirrored by similar attempts in the writings of leading mathematicians. For instance, the very same issues discussed by Hume had already been debated by two leading figures in continental science, D'Alembert and Euler. For his part, in his famous work, D'Alembert expressed a view that is very similar to Hume in certain respects. He proclaimed right at the outset that he wished to develop a physics that would dispense of the concept of a force altogether on the grounds that it was an obscure idea. He would reduce all the principles of mechanics to three: the force of inertia, compound motion, and equilibrium. He immediately explained the first item. The reason that he could accept Newton's force of inertia is that it's characterized as a property of bodies, one in virtue of which they follow the laws of motion, rather than a force of power, so it was not an obscure notion. Ironically, the great Swiss mathematician Euler had precisely the opposite reaction. From his point of view, the force of inertia was simply a misnomer, for it was not a force at all, and should therefore be expunged from physics altogether. Instead, physics should employ only the idea of an impressed force, a cause of acceleration, which he regarded as a perfectly clear idea. Of course, history was on Euler's side. Indeed, so much of the future generations would not even imagine that so many leading philosophers and mathematicians during the Enlightenment debated this topic. In other respects, in France, the intellectual situation was rather different than in England. Cartesian ideas held sway for many decades after Newton first emerged on the scene in the 1670s with his optics paper, and in the late 1680s with the Principia. They were especially popular at the Academy Royal, the Royal Sciences, unlike the situations in the Royal Society of London. Voltaire became famous for challenging the Cartesian French orthodoxy, traveling to England for a celebrated visit and bringing home enlightened ideas about philosophy, politics, and much else, besides an attempt to foment the emergence and development of a French Newtonian program. His most important publication in this regard, probably The Elements of the Philosophy of Newton, which attempts to signal the errors of Descartes and to highlight the advantage of the Newtonian program in physics. Of course, Cartesian ideas and methods retained numerous adherents and defenders in France, and so the debate between Cartesians and Newtonian ideas flourished in that environment. But even in France, Cartesians eventually gave way to the newer version of metaphysics associated with Leibniz and his German follower and expositor Wolff. In 1740, Émile de Châtelet published a key text, Foundations of Physics, inner text, which was republished in a second edition in 1742 and swiftly translated into German and Italian. She makes precisely the kind of argument that presses Hume a few years later to articulate a conception of vis inertia that is consistent with the experimental philosophy. She argues that the Cartesian view that extension is the essence of body is mistaken. We must conceive of material objects as exhibiting a force of inertia if we are to understand their physical interactions properly. Perhaps not surprisingly, D'Alembert cites her text approvingly in his treatise on dynamics. For de Châtelet's point of view, this Newtonian conception of body is not inherently problematic. Problems arise, however, when some Newtonians interpret the theory of universal gravity as proving that bodies have a property of attraction or attractive power endowed by God. She accepts the idea that gravity is proportional to the masses of bodies and inversely proportional to the square of their spatial separation, arguing that this Newtonian idea of attraction marvelously explains the fall of bodies on Earth, the tides, the various astronomical phenomena, something that the vortex theory of the Cartesian fails to do. But she denies that acceptance entails that she must also accept the conclusion that the bodies have an essential property called gravity or attractive force, contending that such a conclusion transcends the knowledge available to philosophers. The reason is that no one had yet demonstrated that there is no medium for gravity, such as a vortex or an ether. Since gravity may depend on some medium, it may not be essential to matter per se. In this specific way, Chatelet's work is predicated on the familiar notion that although Cartesianism has been overthrown by Newtonian ideas and methods, philosophers must nonetheless develop a proper interpretation of the Newtonian theory of gravity and of its implications. Yet, unlike Voltaire, who not only rejected Cartesianism but became famous for his ridicule of Leibnizian philosophy in Candide, Chatelet argued that philosophers should continue to work on developing the proper methodology, in part by taking seriously the ideas and methods of Leibniz and Wolff. In particular, Chatelet argued that the principle of sufficient reason should be a guiding force in metaphysical theorizing, and as Leibniz has argued, it showed that fundamental error in Newton's concept of absolute space. She added that Clarke's method of replying to Leibniz's argument that one can develop a non-Leibnizian or voluntarist conception of the principle of sufficient reason to evade the problem of absolute space is underwhelming. She also argued that if we use the principle of sufficient reason to guide our thinking about space, we will be skeptical of Locke's solution to the problem of understanding the philosophical implication of Newton's theory of universal gravity. The idea that Newton's theory supports the conclusion that God must have superadded gravity to matter avoids potential problems with asserting that gravity is essential to matter, something she also regards skeptically but simply encounters other problems. First, since no one yet understood whether there was any medium underlying gravitational interactions, such as an ether, it is premature to conclude that gravity is a property of matter, even one superadded to it by divine fiat. After all, if there is an ether, then matter may gravitate because of its interactions with the ether and not because of any superadded property. Second, the principle of sufficient reason demands that we seek rational explanations of natural phenomena in our science, but the superaddition thesis is predicated on the idea that we simply cannot understand how matter gravitates towards other matter. Newton's science is simply taken to indicate that it does so. She was unwilling to leave the most important conclusion of the scientific revolution a mere mystery. Euler's rejection of the vis inertiae was not only his major reaction to Newton's science. The question of whether to accept and how to interpret absolute space, time, and motion, and the related questions of how to conceive of the relation between Newton's work in the natural philosophy and the flourishing Leibnizian Wolffian metaphysics on the continent continued to drive conversations in the middle 18th century. Just a few years after Chatelet published her Institutions, Euler presented a novel approach to these two questions in a short paper entitled Reflections on the S-space and Attempts, first published in 1748 in the Memoirs de l'Académie de Sciences of Berlin. The Berlin Academy had been witnessing a vociferous debate between Wolffians and Newtonians since 1740, a debate that would continue until roughly 1759, one in which Euler played a role, whereas one might regard the British philosophers, especially Berkeley and Hume, as arguing that philosophical principles and commitments take a kind of precedence in the driving one's interpretation of the concepts of force, motion, space, and time. Euler argued that natural philosophy, specifically mechanics, ought to take precedence. The famous first sentence of his essay indicates why he contends that the principles of mechanics, for instance, the principles of inertia, are so well established that it would be foolish to doubt them. In particular, if one's metaphysical commitment stands in tension with the concepts of space and motion found in geometry and mechanics, then one must adjust those commitments accordingly. Euler then presented a clever argument. The law of inertia picks out a rectilinear motion as a special kind of motion, so to apply it to bodies in nature, there must be a clear meaning to the idea of a straight line, but if space is merely the order of relations amongst material bodies, then any set of reference bodies which we use to determine which motion is straight could itself be in motion. So to employ the idea of rectilinear motion, we required the notion of absolute space. The most important figure in German-speaking Europe to react in depth to Newton's idea was surely Immanuel Kant. As a young man, Kant was influenced by Euler's argument in the 1748 piece. Kant began grappling with Newtonian ideas at the very beginning of his career. He discussed the inverse square law in his first publication, and they would remain central both to his magnum opus, The Critique of Pure Reason, and to his metaphysical foundations of natural science. In the so-called pre-critical period, Kant diverged sharply from the approach towards natural philosophy defended by many Leibnizians in German-speaking Europe by deciding to accept Newtonian theory of universal gravity, along with corresponding aspects of Newtonian conception of matter, as a starting point for the philosophical theorizing. He makes this explicit in his 1763 in The Only Possible Argument. I will attempt to provide an explanation of the origin of the world system according to the general laws of mechanics, not an explanation of the entire natural order, but only of the great masses of matter and their orbits, which constitute the most crudest foundation of nature. I will presuppose the universal gravitation of matter according to Newton or his followers in this project. If there are any who believe that through a definition of metaphysics formulated according to their own taste, they can annihilate the conclusions established by men of capacity on the basis of observation and by means of mathematical inference. If there are any such persons, they can skip the following propositions as something which has only a remote bearing on the main aim of this essay. A rare case of Kantian irony, it seems that already in this early text, Kant has clearly broken with his predecessors in both England and the continent, who insisted on disputing Newton's theory of universal gravity, either on metaphysical or theological grounds. Instead, Kant works will be predicated on that theory, but Kant never became an orthodox Newtonian any more than orthodox Leibnizian and Wolffian. This is evident from the radically different fate of two classic Newtonian concepts within the Kantian system. The idea that the theory of universal gravity shows that gravity is a feature of material bodies, along with the related concept of action at a distance, on the one hand, and absolute space on the other. The quotation from 1763 indicates that Kant was willing to endorse Newton's theory of universal gravity, despite the many objections raised against it in his Leibnizian predecessors. Indeed, he was also willing to accept the most radical interpretation of the last theory, one according to which every material body in the world should be understood as bearing a feature called gravity, one that involves the body in actions at a distance on all other such bodies, as Kant put it dramatically in Proposition 7 of the second chapter of the Metaphysical Foundations of Natural Science. The attraction essential to all matter is immediate action of matter on other matter through empty space. This view is radical in two senses. First, it involves the highly controversial claim that gravity is essential to matter, which indicates that a body lacking gravitational interactions would potentially fail to count as a material entity at all, much as an earlier generation of philosophers would conceive of an extension as essential to matter. And second, it also involves the debated idea that material bodies act at a distance on one another. One can conceivably endorse the latter without endorsing the former, contending that although material bodies in the actual world act at a distance on one another, perhaps because of a divine plan, it is perfectly possible for material bodies to fail to do so under distinct worldly conditions. There may be possible worlds in which material bodies lack gravity altogether. That is, the endorsement of action at a distance does not entail the endorsement of the essentiality claim. Both ideas are controversial, and Kant strongly endorses them both. This placed him in a rather select group of radical Newtonians. Kant himself understood that Newton may not have endorsed these controversial claims, arguing that he was inconsistent on the score, and yet Kant strongly resisted the other more controversial Newtonian idea, absolute space, along with the related idea of absolute motion. In the Critique of Pure Reason, for instance, Kant expressed a basically Leibnizian sympathy by arguing that there are fundamental metaphysical and perhaps epistemic difficulties with thinking of space and time as existing independently of all objects and all possible relations among them as actual entities in their own right. He does this so in a passage that perhaps confusingly characterizes the Leibnizians as also defending a kind of realism about space, but we can focus solely on his criticism of the Newtonians. Those, however, assert the absolute reality of space and time, whether they assume it to be subsisting or only inhering, must themselves come into conflict with the principles of experience. For if they decide in favor of the first, which is generally a position of the mathematical investigators of nature, then they must assume two eternal and infinite subsisting non-entities, space and time, which exist yet without there being anything real, only in order to comprehend everything real within themselves. If one regards space like time as existing independently of all objects and all possible relations, and yet one admits that space is causally inert and imperceptible, as one presumably must in the late 18th century, then one is committed to the idea that there is a kind of infinite and eternal non-entity in the world. Space is a kind of non-entity, Kant suggests, because on the one hand it is said to exist independently of everything else, and yet on the other hand it is said to be causally inert and imperceptible, which would distinguish it from every other sort of thing that exists. Kant simply cannot stomach this metaphysically preposterous notion. It is therefore incumbent upon him to develop a theory of space and motion that meets at least two distinct criteria. One, it coheres with his understanding of the theory of universal gravity and of what he regards as its implication that gravity is an essential feature of material bodies, and two, it avoids the metaphysically problematic aspects of Newtonian absolute space. Kant tackles precisely these tasks in the Metaphysical Foundations, which was published in between the appearances of the first and second edition of the Critique, arguing that we can regard absolute space as a kind of idea of reason, an ideal that we approach asymptotically in our theorizing about motion. Absolute space is therefore nothing more than a kind of ideal within our philosophy and no longer a harmful aspect of our ontology. Newton's influence on the development of philosophy did not end with the close of the 18th century. Most obviously, the concepts of absolute space and absolute motion continued to play a fundamental role in philosophical theorizing about space and motion more generally for the next 2 centuries, and they remain fundamental to discussions today. Newton also had a deep and lasting influence on numerous other topics in what we now call the philosophy of science, including the status of our knowledge of natural phenomena, the best ideas about scientific methodology, the status of the laws of nature, and much else besides. It is no exaggeration to say Newton has a permanent place in the history of modern philosophy. Okay, so that one was really long. Jimmy Hill, God bless, thanks for tuning in. So I will probably do two more. I probably will have to skip. I'll probably have to split it up between today and tomorrow because I have four more, and this one took a really long time. Okay, so check my messages and pour myself another drink and we'll keep at it. So sorry for the break here. Okay, so next we're going to look at we're going to look at space, time, and motion. And we're going to look at two things. We're going to look at a review of classical theories, and then we're going to do a deep dive into Newton's view of space, time, and motion. And I'll probably tomorrow finish with the deep dive into Newton's Principia and Hume's development of the empirical method, because just these three today will probably take over 5 hours. So appreciate Mr. Boston. Just get another drink. Okay. So next, we're going to look at absolute and relational space in motion and classical theories, going from Aristotle, Descartes, Newton, and Leibniz. And so we'll have more detail in these important. So metaphysically, philosophically, there's multiple, but two huge factors in Newton. And one is the development of the empirical method and, say Hume and the application of the empirical method towards morality, towards politics, to other fields besides mathematical physics. And then within the mathematical physics, one of the most important matters is the concept of absolute space and motion. So, I mean, there's obviously other things like action at distance, gravity, the nature of universal laws described by mathematics. But the conceptions of two metaphysics that are extremely important are the concepts of absolute and relational space and motion, space and time, and the overthrow of the historical Cartesian, Aristotelian, scholastic understandings of these. So a lot of people these days are no longer familiar. I mean, they might just know Descartes, or like probably haven't heard of the theories of extension or the old Aristotelian scholastic understandings of space, time, and motion, because the Newtonian had basically became the dominant norm. As he's seen through Immanuel Kant and some of his conceptions, uh, till Einstein. So here we go. Absolute and relational space and motion classical theories. Since antiquity, natural philosophers have struggled to comprehend the nature of the three tightly interconnected concepts, space, time, and motion. A proper understanding of motion, in particular, has been seen to be crucial for deciding questions about the nature of space and time and their interconnection. Since the time of Newton and Leibniz, philosophers' struggles to comprehend these concepts have often appeared to take the form of a dispute between absolute conceptions of space, time, and motion and relational conceptions. This article guides the reader through some of the history of these philosophical struggles. Rather than taking sides in the alleged ongoing debates or reproducing the standard dialectic recounted in most introductory texts, we have chosen to scrutinize carefully the history of the thinking of the canonical participants in these debates, principally Descartes, Newton, Leibniz, Mach, and Einstein. Introduction. Things change. This is a platitude, but still a crucial feature of the world, and one which causes many philosophical perplexities, since for instance, the entry Zeno's paradox for Aristotle, motion, he would have called it locomotion, was just one kind of change, like generation, growth, decay, fabrication, and so on. The atomist held that, on the contrary, that all change was in reality the motion of atoms into new configurations, an idea that was not to begin to realize its full potential until the 17th century, particularly in the work of Descartes. Of course, modern physics seems to show that the physical state of a system goes well beyond the geometric configuration of bodies. Fields, well, perhaps determined by the states of bodies, are not themselves configurations of bodies if interpreted literally, and in quantum mechanics, bodies have inertial states such as particle spin. Not all change seems to be merely the locomotion of bodies in physical space, yet since antiquity in the Western tradition, this kind of motion had been absolutely central to the understanding of change. And since motion is a crucial concept in physical theories, one is forced to address the question of what exactly it is. The question might seem trivial, for surely what is usually meant by saying that something is moving is that it is moving relative to something, often tacitly understood between speakers. For instance, the car is moving at 60 miles per hour relative to the road and things along it. The plane is flying relative to London. The rocket is lifting off the ground, or the passenger is moving to the front of the speeding train. Typically, the relative reference body is either the surroundings of the speakers or the Earth, but this is not always the case. For instance, it seems to make sense to ask whether the Earth rotates around its axis west-east diurnally, or whether it instead the heavens that rotate east-west. But if all motions are to be reckoned relative to Earth, then its rotation seems impossible. But even if Earth does not offer a unique frame of reference for the description of motion, then we may wonder whether any arbitrary object can be used for the definition of motion, and all such motions are on a par, none privileged over any other. It is unclear whether anyone has really consistently espoused this view. Aristotle, perhaps, in the Metaphysics, Descartes, and Leibniz are often thought to have done so. However, as we shall see, these claims are suspect, possibly Huygens, though the most recent and thorough reconstruction of his position indicates not. Mach, at some moments, perhaps. If this view were correct, then the question of whether the earth or heavens rotate would be ill-formed, those alternatives being merely different but equivalent expressions of the facts. However, suppose, like Aristotle, you take ordinary language accurately to reflect the structure of the world, then you could recognize systematic everyday uses of up and down that require some privileged standards, uses that treat things closer to a point of the center of Earth as more down and motions towards that point as downwards. Of course, we would like They explain this usage in terms of the fact that we and our language evolved in a very noticeable gravitational field directed towards the center of the Earth. But for Aristotle, as we shall see, this usage helped identify an important structural feature of the universe, which itself was required for the explanation of weight. Now, a further question arises: how should a structure such as a preferred point in the universe, which privileges certain motions, be understood? What makes that point privileged? One might expect that Aristotle simply identified it with the center of the Earth, and so relative to that particular body. However, we shall soon see that he did not adopt that tacit convention as fundamental. So the question arises of whether the preferred point is somewhere picked out in some other way by the bodies of the universe, the center of the heavens perhaps, or is it picked out quite independently of the arrangements of matter? The issues that arise in this simple theory help to frame the debates between the latter physicists and philosophers concerning the nature of motion. In this article, we will focus on the theories of Descartes, Leibniz, and Newton. In the companion entry on absolute and relational space and motion post-Newtonian theories, we study the approaches followed by Mach and Einstein and certain contemporary researchers. We will see that similar concerns pervade all of these works. If there is any kind of privileged sense of motion, a sense in which things can be said to move or not just relative to this or that reference body, but truly, if so, can this true motion be analyzed in terms of motions relative to other bodies, to some special body, or to the entire universe, perhaps? And in relativity, in which distances, times, and measures of relative motion are frame dependent, what relations are relevant? If not, then how is the privileged kind of motion to be understood as relative to space itself, something physical but non-material perhaps, or can some kind of motion be best understood as not being spatial changes of relative location or of place at all? Aristotle. Do you see that the problem of the interpretation of spatial temporal quantities as absolute or relative is endemic to almost any kind of mechanics one can imagine? We could look at one of the simplest theories, Aristotle's account of natural motion. According to this theory, it is because of their natures and not because of unnatural forces that the heavenly bodies move down and light things, air and fire, move up. It is their natures or forms that constitute the gravity or weight of the former and the levity of the latter. This account only makes sense if up and down can be unequivocally determined for each body. Accordingly to Aristotle, up and down are fixed by the position of the body in question relative to the center of the universe, a point coincident with the center of the Earth. That is, the theory holds that heavy bodies naturally move towards the center, while lighter bodies naturally move away. Does this theory involve absolute or merely relative quantities? It depends on the nature of the center. If the center were identified with the center of Earth, then the theory could be taken to eschew absolute quantities. It would simply hold that natural motions of any body depend on the position relative to another, namely the Earth. But Aristotle is explicit that the center of the universe is not identical with, but merely coincident with the center of the Earth. Since the Earth itself is heavy, if it were not at the center, it would move there. So the center is not identified with any body, and so perhaps directional to center is an absolute quantity in the theory, not understood fundamentally as a direction to some body, merely contingent as such if some body happens to occupy the center. But this conclusion is not clear either. And on the heavens, admittedly in response to a different issue, Aristotle suggests that the center itself is determined by the outer spherical shell of the universe, the ethereal region of the fixed stars. If this is what he intends, then the natural law prescribes motion relative to another body after all, namely up and down with respect to the mathematical center of the stars. It would be to push Aristotle's writing too hard to suggest that he was consciously wrestling with the issue of whether mechanics requires absolute or relative quantities of motion, but what is clear is that these questions arise in his physics and his remarks impinge upon them. His theory also gives a simple model of how they arise, a physical theory of motion. We'll say that under such and such circumstances, motion and so a kind will occur. And the question of whether that kind of motion makes sense in terms of the relation between bodies alone arises automatically. Aristotle may not have recognized the question explicitly, but he sees it as one issue in the background of his discussion of the center of the universe. Descartes. The issues are, however, far more explicit in the entry on Descartes' physics, and since the form of the theory is different, the kinds of motion in question are quite different, as they change with all the different theories that we discussed. For Descartes argues 1644 Principles of Philosophy that the essence of matter is extension, size, and shape, because any other attribute of bodies could be imagined away without imagining away matter itself. But he also held that extension constitutes the nature of space, and hence he concludes that space and matter are one and the same thing. An immediate consequence of this identification is the impossibility of the vacuum. If every region of space is a region of matter, then there can be no space without matter. Thus, Descartes' universe is a hydrodynamical, completely full of mobile matter of different sized pieces in motion, rather like a bucket full of water and lumps of ice in different sizes, which has been stirred around. Since fundamentally the pieces of matter are nothing but extension, the universe is in fact nothing but a system of geometric bodies in motion without any gaps. The nature of motion. The identification of space and matter poses a puzzle about motion. If the space that a body occupies literally is the matter of the body, then when the matter moves, so does the space that it occupies. Thus, it doesn't change place, which is to say that it doesn't move at all. Descartes resolved this difficulty by taking all motion to be the motion of bodies relative to one another, not a linear change of space. Now, a body has many relative motions as there are bodies, but it does not follow that all are equally significant. And Descartes uses several different conceptual concepts of relational movement. First, there is changes in place, which is nothing but motion relative to this or that arbitrary reference body. In this sense, no motion of a body is privileged, since the speed, direction, and even curve of trajectory depends on the reference body, and none is singled out. Next, he discusses motion in the ordinary sense. This is often conflated with mere change of arbitrary place, but strictly it differs because, according to the rules of ordinary speech, one correctly attributes motion only to bodies whose motion is caused by some action, not to arbitrary relative motion. For instance, a person sitting on a speeding boat is ordinarily said to be at rest, since he feels no action on himself. This distinction is important in some passages, but arguably not in those that we discuss. Finally, he defines motion, properly speaking, to be the transference of one part of matter or of one body from the vicinity of those bodies immediately contiguous to it and considered at rest into the vicinity of some other. Since a body can only be touching one set of surrounding, Descartes argued questionably that this standard of motion was unique. What we see here is Descartes, despite holding motion to be the motions of bodies relative to one another, also held that there is a privileged sense of motion in a terminology sometimes employed by writers of the period. He held there is a sense of true motion over and above merely relative motion. In logical terms, we can make the point this way. Well, moves relative to is a two-place predicate, moves properly speaking in a one-place predicate, and this, even though it is defined in terms of relative motion, let contiguous surroundings be functional from bodies to their contiguous surroundings, then x moves properly speaking is defined as x moves relative to contiguous surroundings. This example illustrates why it is crucial to keep two questions distinct. On the one hand, is motion to be understood in terms of relations between bodies or as invoking something additional, something absolute? On the other hand, are all relative motions equally significant, or is there some true privileged notion of motion? Descartes' views show that eschewing absolute motion is logically compatible with accepting true motion, which is, of course, not to say that his definitions of motions are themselves tenable. Motion and dynamics. There's an interpretation of tradition that holds Descartes only took the first ordinary sense of motion seriously and introduced the second notion to avoid conflict with the Catholic Church. Such conflict was a real concern since the censure of Galileo's Copernicanism took place only 11 years before the publication of Principles, and had in fact dissuaded Descartes from publishing an earlier work, The World. Indeed, in the Principles, he is at pains to explain how, properly speaking, the Earth does not move because it is swept around the sun in a giant vortex of matter. The Earth does not move relative to its surrounding in the vortex. The difficulty with the reading, aside from the imputation of cowardice to the old soldier, is that it makes nonsense of Descartes' mechanics a theory of collision. For instance, according to his laws of collision, if two bodies strike each other at equal or opposite velocities when they bounce off at equal and opposite velocities. On the other hand, if the very same bodies approach each other with the very same relative speed, but at a different speeds, then they will move off together in the direction of the faster one. But if the operative meaning of motion in the rules is the ordinary sense, then these two situations are just the same situation, differing only in the choices of reference frame, so could not have different outcomes, bouncing apart versus moving off together. It seems inconceivable that Descartes could have been confused in such a trivial way. Thus, Garber proposes that Descartes actually took the unequivocal notion of motion, properly speaking, to be the correct sense of motion in mechanics. Then Rule 1 covers the case in which two bodies have equal and opposite motions relative to the contiguous surroundings, while Rule 6 covers the case in which bodies have different motions relative to those surroundings. One is perhaps at rest in its surroundings. That is exactly what is needed to make the rules consistent in the kind of privileged true sense of motion provided by Descartes' second definition. Insurmountable problems with the rules remain, but rejecting the traditional interpretations and taking motion, properly speaking, seriously in Descartes' philosophy clearly gives a more charitable reading. Newton articulated a clearer, more coherent, and more physically plausible account of motion than any that had come before. Still, as we see, there have been a number of widely held misunderstandings of Newton's view, and it is not completely clear how to best understand the absolute space that he postulated. Newton against the Cartesian account of motion, the bucket. In an unpublished essay, De Gravitatione, and in a scholium to the definitions given in 1687, Mathematical Principles of Natural Philosophy, Newton attacked both of Descartes' notion of motion as candidates for the operative notion in mechanics. The most famous argument invokes the so-called Newton bucket experiment. Stripped to its basic elements, one compares a bucket of water hanging from a cord as a bucket is set spinning around about the cord's axis with the same bucket and water when they are rotating at the same rate about the cord's axis. As is familiar with any rotating system, there will be a tendency for the water to recede from the axis of rotation in the latter case, and the surface of the water will be flat because the Earth's gravitational field. When the second case, it will be concave. The analysis of such inertial effects due to rotation was a major topic in the inquiry of natural philosophers at the time, including Descartes and his followers, and they would certainly have agreed with Newton that the concave surface of the water in the second case demonstrated that the water was moving in a mechanically significant sense. There is thus an immediate problem to the claim that proper motion is the correct mechanical sense of motion. In both cases, proper motion is anti-correlated with the mechanically significant motion revealed by the surface of the water. That is, the water is flat in the first case when it is in motion relative to its immediate surrounding in the inner sides of the bucket, but curved in case 2 when it is at rest relative to its immediate surroundings. Thus, the mechanically relevant meaning of rotation is not that of proper motion. You may have noticed a small lacuna in Newton's argument. In case 1, the water is at rest, and in case 2, the motion relative to that part of the surrounding constituted by the air above it. It's not hard to imagine small modifications to the example to fill this gap. Newton also points out that the height of the water climbs up inside the bucket provides a measure of the rate of rotation of the bucket in the water. The higher the water rises up inside, the greater the tendency to recede must be, and so the faster the water must be rotating in the mechanically significant sense. But suppose very plausibly that the measure is unique, that any particular height indicates a particular rate of rotation, then the unique height that the water reaches at any moment implies a unique rate of rotation in a mechanically significant sense, and thus motion in the sense of motion relative to an arbitrary reference body is not the mechanical sense, since that kind of rotation is not unique at all, but depends on the motion of a reference body. And so Descartes changed of place, and for similar reasons, motion in the ordinary sense is not the mechanically significant sense of motion. Absolute space and motion. In our discussion of Descartes, we called the sense of motion operative in the science of mechanics true motion, and the phrase is used in this way by Newton in the scholium. Thus, Newton's bucket shows that the true rotational motion is anti-correlated with, and so not identical with proper motion as Descartes proposed according to the Garber reading. And Newton further argued that the rate of true rotational motion is unique, and so not identical with change of place, which is multiple. Newton proposed instead that true motion is a motion relative to temporal enduring, rigid three-dimensional Euclidean space, which he dubbed absolute space. Of course, Descartes also defined motion as relative to an enduring three-dimensional Euclidean space. The difference is that Descartes' space was divided into parts. His space was identical with a plenum of corpuscles in motion, not a rigid structure in which mobile material bodies are embedded. So according to Newton, the rate of true rotation of the bucket and water is the rate at which it rotates relative to absolute space. Or put it another way, Newton effectively defines one place predicate x moves absolutely as x moves relative to absolute space. Both Newton and Descartes offers completing one place predicates as analysis of X moves truly. Absolute space versus Galilean relativity. Newton's proposal for understanding motion solves the problems that he posed for Descartes and provides an interpretation of the concepts of constant motion and acceleration that appear in his laws of motion. However, it suffers from the two notable interpretation problems, both which were pressed forcefully by Leibniz and the Leibniz-Clark correspondence 1715-16, which is not to say that Leibniz himself offered a superior account of motion. First, according to this account, absolute velocity is a well-defined quantity. More simply, the absolute speed of a body is the rate of change of its position relative to an arbitrary point in absolute space. But the Galilean relativity of Newton's laws means that the evolution of a closed system would have to be identical if it had been moving at a different constant overall velocity, as Galileo noted in his an experimenter cannot determine from observation inside the cabin whether his ship is at rest in harbor or sailing smoothly. Put another way, according to Newtonian mechanics, in principle, Newton's absolute velocity cannot be experimentally determined. So in this regard, absolute velocity is quite unlike acceleration, including rotational. Newton's acceleration is understood in absolute space as the rate of change of absolute velocity and is, according to Newtonian mechanics, generally measurable, for instance, by measuring the height that the water ascends to the side of the buckets. Leibniz argued rather inconsistently, as we shall see, that since differences in absolute velocity are unobservable, they are not to be genuine differences at all, and hence that Newton's absolute space, whose existence would entail the reality of such differences, must also be a fiction. Few philosophers today would immediately reject a quantity as unreal simply because it was not experimentally determinable, but this fact does justify genuine doubts about the reality of absolute velocity and hence of absolute space. The ontology of absolute space. The second problem concerns the nature of absolute space. Newton quite clearly distinguishes his account from Descartes, and in particular with regards to absolute space rigidity versus Descartes' hydrodynamical space and the possibility of the vacuum in absolute space. Thus, absolute space is definitely not material. On the other hand, presumably, it is supposed to be part of the physical, not mental realm. In gravity, Newton rejected both the traditional philosophical categories of substance and attribute as suitable characterization. Absolute space is not a substance, for it lacks causal powers and does not have a fully independent existence, and yet it is not an attribute since it would exist even in a vacuum, which by definition is a place where there are no bodies in which it might inhere. Newton proposes that space is what we might call a pseudo-substance, more like a substance than a property, yet not quite a substance. In fact, Newton accepted the principle that everything that exists somewhere in absolute space. Thus, he viewed absolute space as a necessary consequence of the existence of anything, and of God's existence in particular. Hence, space's ontological dependence. Leibniz was presumably unaware of the unpublished De Gravitatione in which these particular ideas were developed, but as we shall see, his later works are characterized by robust projection of any notion of space as a real thing rather than an ideal, purely mental entity. This is the view that attracts even fewer contemporary adherents, but there is something deeply peculiar about the non-material but physical entity, a worry that has influenced many philosophical opponents of absolute space. Newtonian absolute space in the 20th century. This article is largely a historical survey of the prominent views. However, it is hard to fully understand those debates without knowing something about the scientific and mathematical developments have changed recent understandings of the issues. In particular, a space-time approach can clarify the situation in which the interlocutors were wrestling and help clarify their arguments. This is a point widely recognized in the secondary literature and indeed colors much of what is said there for good and bad, as we shall touch on later. So a short digression into these matters is important for engaging the literature responsibly. That is, section 7 presupposes this section. The reader only interested in section 6 could skip this section. The space-time approach. After the development of relativity theory, a topic that we address in the companion article, and its interpretation of space-time theory, it was realized that the notion of space-time had applicability to a range of theories of mechanics, classical as well as relativistic. In particular, there is space-time geometry, Galilean or neo-Newtonian space-time. The terms are interchangeable. For Newtonian mechanics, that solves the problem of absolute velocity, an idea exploited by a number of philosophers from the late 1960s onward. The general idea is that although a spatial distance is well defined between any two simultaneous points on space-time, only the temporal interview is well defined between non-simultaneous points. Thus, things are rather unlike Newton's absolute space, whose points persist throughout time and maintain their distance. In absolute space, the distance between P now and Q then, where P and Q are points, is just the distance between P now and Q now. However, Galilean spacetime has an affine connection which effectively specifies for every point of the continuous curve the rate at which the curve is changing from straightness to at that point. For instance, the straight lines are picked out as those curves whose rate of change from straightness is zero at every point. Since the trajectories of bodies are curves in the spacetime, the affine connection determines the rate of change from straightness at every point of every possible trajectory. The straight trajectories are thus defined can be interpreted as the trajectories of bodies moving inertially without forces, and the rate of changes from straightness and the trajectories can be interpreted as the acceleration of bodies following that trajectory. That is, Newton's first law can be given a geometric formulation as bodies on which no net forces act follow straight lines in spacetime. Similarly, the second law can be formulated as the rate of changes from straightness of a body's trajectory is equal to the forces acting on the body divided by its mass. The significance of this geometry is that while acceleration is well defined, velocity is not. In accordance with the empirical determinability of acceleration, generally, though not universally, but not of velocities, according to Newtonian mechanics, thus Galilean spacetime gives a very nice interpretation of the choice that nature makes when it decides that the laws of mechanics should be formulated in terms of acceleration, not velocity. In fact, there are complications here. In light of Newton's corollary 6 mentioned above, one might wonder whether even Galilean spacetime is the appropriate spacetime structure for Newtonian mechanics. Saunders, for example, argues that this fact only a yet more impoverished spacetime structure, Newton-Huygens spacetime, is needed. Substantialism. Put another way, one can define the predicate x accelerates as trajectory x has non-zero rate of change from straightness, where trajectory maps embodied onto their trajectories in Galilean spacetime. And this predicate defined this way applies to the water in Newton's bucket if and only if it is rotating according to Newtonian mechanics formulated in terms of the geometry of Galilean spacetime. It is the mechanically relevant sense of accelerate in this theory, but this theoretical formulation and definition has been given in terms of the geometry of spacetime, not in terms of the relations between bodies. Acceleration is absolute in the sense that it is a preferred true sense of acceleration mechanics, in which it is not defined in terms of motions of bodies relative to one another. Note that this sense of absolute is broader than the motion relative to absolute space, which we defined earlier. In the remainder of this article, we will use it in this new broader sense. The reader should be aware that the term is used in many ways in the literature, and such equivocation often leads to significant misunderstanding. If any of this analysis of motion is taken literally, then one arrives at a position regarding the ontology of spacetime rather like that of Newton's regarding space. It is some kind of substantial or maybe pseudo-substantial thing with the geometry of Galilean spacetime, just as the absolute space possessed Euclidean geometry. This view regarding the ontology of spacetime is usually called substantialism. The Galilean substantialism usually sees themselves as adopting a more sophisticated geometry than Newton, but sharing his substantialism. The advantage of the more sophisticated geometry is that although it allows the absolute space sense of acceleration apparently required by Newtonian mechanics to be defined, it does not allow one to define a similar absolute speed of velocities. X accelerates can be defined as a one-place predicate in terms of the geometry of Galilean spacetime, but not X moves in general. And so the first of Leibniz's problems is resolved. Of course, we see that the solution depends on a crucial shift from speed and velocity to accelerate as the relevant sense of motion, from the rate of change of a position to the rate of change. While this proposal solves the first kind of problem posed by Leibniz, it seems just as vulnerable to the second. Whether it's true that it involves the rejection of absolute space as Newton conceived it, and with the need to explicate the nature of an enduring space, the postulation of Galilean spacetime poses the parallel question of the nature of spacetime. Again, it is a physical but non-material something, the point of which may be coincident with material bodies. What kind of thing is it? Could we do without it? As we shall see below, some contemporary philosophers believe so. Leibniz. There is a folk reading of Leibniz that often finds either explicitly or implicitly in the philosophy of physics literature, which takes account of only some of his remarks on space and motion. For instance, the quantities captured in Ehrman's 1999 Leibnizian spacetime do not do justice to Leibniz's view of motion, as Ehrman acknowledged, but is perhaps most obvious in introductory text. According to this view, the only quantities of motion are relative quantities, relative velocity, acceleration, and so on, and all relative motions are equal, and there's no true sense of motion. However, Leibniz is explicit that other quantities are also real, and his mechanics implicitly, but obviously depends on yet others. The length of this section is a measure not so much of the importance of Leibniz's actual views, but the importance of showing what the prevalent folk view leaves out regarding Leibniz's views on the metaphysics of motion and interpretation of mechanics. That said, we shall also see that no one has yet discovered a fully satisfactory way of reconciling the numerous conflicting things that Leibniz says about motion. Some of these tensions can be put down simply to his changing his mind. However, we will concentrate on the fairly short period in the mid-1680s to 90s during which Leibniz developed his theory of mechanics and was mostly concerned with its interpretation. We will supplement this discussion with the important remarks that he made in his correspondence with Samuel Clarke about 30 years later. This discussion is broadly in line with the earlier period and the intervening period in which he turned to other matters rather than one in which the views of his space were evolved dramatically. The ideality of space. Arguably, Leibniz's views concerning space and motion do not have a completely linear logic, starting with some logically sufficient basic premises, but instead from a collection of mutually supporting doctrines. If one starts questioning why Leibniz held certain views concerning the ideality of space, for instance, one is apt to be led in a circle. Still, exposition requires starting somewhere, and Leibniz's arguments for the ideality of space in the correspondence with Clarke is a good place to begin. But bear in mind the caveats made here. This argument was made later than a number of other relevant writings, and its logical relation to Leibniz's views on motion is complex. Leibniz says that a body comes to have its same place as another once did when it comes to stand in the same relation. Two bodies we suppose to be unchanged. More on that later, that we can define a place to be that which any such two bodies have in common. Here he claims an analogy with the Euclidean Eudoxian definition of a rational number in terms of the identity relation between ratios, and finally that space is all such places taken together. However, he also holds that properties are particular, incapable of being instantiated by more than one individual, even at different times. Hence, it is impossible for the two bodies to be literally in the same relation to the unchanged bodies. Thus, the thing that we take to be the same for the two bodies, the place, is something added by our minds to the situation and only ideal. As a result, space, which is constructed from the ideal places, is itself ideal, a certain order where the mind conceives the application of relations. Contrast this view with space with those of Descartes and of Newton. Both Descartes and Newton claim that space is a real mind-independent entity. For Descartes, it is a matter, and for Newton, a pseudo-substance distinct from matter. And of course, for both, these views are intimately tied up with the accounts of motion. Leibniz simply denies that mind-independent reality of space, and this too is bound up with his views concerning motion, force, and the nature of motion. So far, apart from the remark about unchanged bodies, we have not seen Leibniz introduce anything more than relations of distance between bodies, which is certainly consistent with this folk view of philosophy. However, Leibniz sought to provide a foundation for the Cartesian mechanical philosophy in terms of the Aristotelian scholastic metaphysics of substantial forms. Here we discuss his views laid out in sections 17 to 22 of the 1686 Discourse on Metaphysics and the 1695 Specimen on Dynamics, both in Garber and Eru, 1989, and particularly defines primary matter in what he calls its primitive passive force of resistance to change in motion and to penetration, and the substantial form of the body, which is primitive action force. It is important to realize that these forces are not mere properties of matter, but actually constituted in some sense, and further that they are not themselves quantifiable. However, because of the collision of bodies with one another, these forces suffer limitation, and derivative passive and active forces result. Derivative passive forces show up in different degrees of resistance to change in different kinds of matter, of secondary matter, in scholastic terms, and apparently is measurable. Derivative active force, however, is considerably more problematic for Leibniz. On the one hand, it is fundamental to his account of motion and theory of mechanics. Motion fundamentally is possession of force, but on the other hand, Leibniz endorses the mechanical philosophy, which precisely sought to abolish Aristotelian substantial form, which active force represents. Leibniz's goal was to reconcile the two philosophers by providing an Aristotelian metaphysical foundation for modern mechanical science. As we shall see, it is ultimately an open question exactly how Leibniz intended to deal with the inherent tension in such a view. Vis viva and true motion. The texts are sufficiently ambiguous to permit dissent, but arguably Leibniz intends that one manifestation of the derivative active forces in what he calls vis viva living force. Leibniz had a famous argument with the Cartesians over the correct definition of this quantity. Descartes defined it as size times speed, effectively as the magnitude of the momentum of a body. Leibniz gave a brilliant argument that it was size times speed squared, so proportional to kinetic energy. If the proposed identification is correct that kinetic energy quantifies derivative action force according to Leibniz, or looked at the other way, the quantity of virtus, another term used by Leibniz for active force, associated with a body determines its kinetic energy and hence its speed. As far as the authors know, Leibniz never explicitly says anything conclusively about the reality of virtus, but it's certainly consistent to read him to claim that there is a unique quantity of virtus and hence true, as we've been using the terms speed associated with each body. At the very least, Leibniz does say that there is a real difference between possession and non-possession of vis viva, and it is a small step from there to true privileged speed. Indeed, for Leibniz, mere change to relative position is not entirely real, as we saw in the instance of the correspondence, and only when it has vis viva as its immediate cause is there some reality to it. An alternative interpretation is the one suggested here, might say that Leibniz intends that while there is a difference between motion virtus and no motion virtus, there is somehow no difference between any strictly positive values of those quantities. It is important to emphasize 2 points about the preceding accounts of motion in Leibniz philosophy. First, motion in the everyday sense. Motion relative to something else is not real. Fundamentally, motion is possession of virtus, something that is ultimately non-spatial, modulo its interpretation as a primitive force limited by collision. If this reading is right, and something along these lines seems necessary, if we aren't simply to ignore the important statement by Leibniz on motion, then Leibniz is offering an interpretation of motion that is radically different from the obvious understanding. One might even say that Leibniz motion is not movement at all. We will leave to one side the question of whether his account is ultimately coherent. The second point is that, however we should understand Leibniz, the folk reading simply does not and cannot take account of his clearly and repeatedly stated view that what is real in motion is force, not relative motion. For the folk reading allows Leibniz only relative motion, and of course, additionally, motion in the sense of force is a variety of true motion, again, contrary to the folk reading. Motion and dynamics. However, from what has been said so far, it is still possible that the folk reading is accurate when it comes to Leibniz's view on the phenomenon of motion, the subject of his theory of mechanics. The case for the folk reading is, in fact, supported by Leibniz's resolution of the tensions that we mentioned earlier between the fundamental role of force virtus, which we will now take to mean mass times speed square, and its association with Aristotelian form. Leibniz's way out specimen in dynamics is to require that while considerations of force must somehow determine the form of the laws of motion, the laws themselves should be such as not to allow one to determine the value of the force and hence true speed. One might conclude that this is the case. Leibniz held that the only quantities which can be determined are those relative position and motion, as the folk reading says, but even in this circumscribed context, it is best questionable whether the interpretation is correct. Leibniz's mechanics. Consider Leibniz's mechanics, since his laws are what is now ironically often called Newtonian elastic collision theory. It seemed that they satisfy both his requirements. The laws include conservation of kinetic energy, which we identify with virtus, but they hold in all inertial frames, so the kinetic energy of any arbitrary body can be set to any initial value, but they do not permit the kinetic energy of a body to take on any values throughout a process. The laws are only Galilean relativistic, and so are not true in every frame. Furthermore, according to the laws of collision in an inertial frame, if the body does not collide, then its Leibnizian force is conserved, while if, except for the special cases, it does collide, then its forces change. According to Leibniz laws, one cannot determine initial kinetic energies, but one certainly can tell when they change. At the very least, they are quantities of motion implicit in Leibniz mechanics, change in force and true speed that are not merely relative. The folk reading is committed to Leibniz simply missing the obvious fact. The equivalence of hypotheses. That said, when Leibniz discusses the relativity of motion, which he calls the equivalencies of hypotheses about the states of motions of bodies. Some of his statements do suggest that he was confused in this way. For another way of stating the problem for the folk reading is that the claim that relative motion alone suffices for mechanics and that all relative motions are on par in a principle in general relativity. And could Leibniz, a mathematical genius, really have failed to notice that his laws hold only in special frames? Well, just maybe. On the one hand, when he explicitly articulates the principle of equivalence of hypothesis, for instance, in specimens of dynamics, he tends to say only that one cannot assign initial velocities on the basis of outcome of a collision which requires only Galilean relativity. However, he confusingly also claimed on Copernicanism and the relativity of motion that the Tychonian and Copernican hypotheses were equivalent, but if the Earth orbits the Sun in an inertial frame, Copernicus, then there is no inertial frame according to which the Sun orbits the Earth, Tycho Brahe, and vice versa. These hypotheses are simply not Galilean equivalent, something else Leibniz could hardly have failed to realize. So there's some sort of textual support for Leibniz endorsing general relativity for the phenomenon, as the folk reading maintains. A number of commentators have suggested solutions to the puzzle of the conflicting pronouncements that Leibniz makes in his subject. Stein, 1977, argues for general relativity, thereby imputing a misunderstanding of his own laws to Leibniz. Roberts, 2003, argues for Galilean relativity, thereby discounting Leibniz's apparent statement to the contrary. Jornig, 2004 and 8, points out the specimen Leibniz claims that all motions are composed of uniform rectilinear motions, and apparently curvilinear motion is actually a series of uniform motions punctuated by discontinuous collisions. This observation allows one to restrict the scope of claims of the kind no motion can be attributed on the basis of phenomenon to internal motions, and so helps read Leibniz as more consistently advocating Galilean relativity. The reading Jarnig favors. See also Huggett's 2006, Can Spacetime Help Settle Any Issues in Modern Philosophy? Note that even in the pure collision dynamics, the phenomenon distinguishes a body in uniform rectilinear motion over time from one that undergoes collisions changing in uniform rectilinear motion over time. The laws will hold in the frame of the former, but not in the frame of the latter. This is apparently contrary to what Jernik says. Leibniz's account of curvilinear motion does not collapse Galilean relativity into general relativity. In that case, Leibniz's specific claim of the phenomenal equivalence of Copernican and Tychonic hypotheses still need to be accommodated. Where did the folk go wrong? So the folk reading simply ignores Leibniz's metaphysics of motion. It commits Leibniz to a mathematical howler regarding his laws, and is arguable whether is the best rendering of his pronouncements concerning relativity. It certainly cannot be accepted unquestionably. However, it is not hard to understand the temptation of the folk reading. In his correspondence with Clarke, Leibniz says that he believes space to be something merely relative as time is, an order of coexistence as time is an order of successions, which is naturally taken to mean that space is at base nothing but the distance and temporal relations between bodies, though even this passage has its subtleness because of the identity of space discussed above, and because in Leibniz's conception space determines what sets of relations are possible, and if relative distances and times exhaust the spatial temporal in this way, then should all quantities of motion be defined in terms of those relations. We have seen two ways in which this would be the wrong conclusion to draw. Force seems to involve a notion of speed that is not identified with any relative speed, and unless the equivalence of hypothesis is, after all, the principle of general relativity, the laws pick out a standard of constant motion that need not be any constant relative motion. Of course, it is hard to reconcile these quantities with the view of space and time that Leibniz proposes. What is speed in size times speed squared, or constant speed, if not speed relative to some body or absolute space, given Leibniz's view that space is literally ideal, and indeed that even relative motion is not entirely real? Perhaps the best answer is that he took force, and hence motion, in its real sense, not to be determined by motion in a relative sense at all, but to be a primitive monadic quantities. This is, he took x moves to be a one-place predicate, but he believed that it could be finally analyzed in terms of a strictly monadic predicate, x moves if and only if x possesses non-zero derivative active force. And this reading explains just what Leibniz took us to be supposing when we suppose certain bodies to be unchanged in the construction of the idea of space. Thus, they had no force, nothing causing or making real any motion. Leibniz's response to Newton's scholium. It's again helpful to compare Leibniz with Descartes and Newton, this time regarding motion. Commentators often express frustration at Leibniz's response to Newton's arguments for absolute space. I find nothing in the scholium that provides or can prove the reality of space in itself. However, I grant that there is a difference between an absolute true motion of a body and a mere relative change. Not only does Leibniz apparently fail to take the argument seriously, he then goes on to concede the step in the argument that seems to require absolute space. But with our understanding of Newton and Leibniz, we can see that what he says makes perfect sense, or at least that it is not as disingenuous as it is often taken to be. Newton argues in the scholium that true motion cannot be identified with the kinds of motion that Descartes considers, but both of these are purely relative motions, and Leibniz is in complete agreement that merely relative motions are not true, entirely real. Leibniz's concession merely registers his agreement with Newton against Descartes on the difference between true and relative motion. He surely understood who and what Newton was refuting, and it is a position that he had himself, in different terms, publicly argued against at length. But as we have seen, Leibniz had a very different analysis of the difference to Newton's. True motion was not for him a matter of motion relative to absolute space, but the possession of a quantity of force ontologically prior to any spatial-temporal quantities at all. There is indeed nothing in the scholium explicitly directed against this view, and since it does potentially offer an alternative way of understanding true motion, it is not unreasonable for Leibniz to claim that there is no deductive inference from true motion to absolute space. Non-Newton versus B. Leibniz. Non sequiturs mistakenly attributed to Newton. The folk reading which belies Leibniz has it that he sought a theory of mechanics formulated in terms only of the relation between bodies. As we'll see in the companion article in the 19th century, Ernst Mach indeed proposed such an approach, but Leibniz clearly did not. Though certain similarities between Leibniz and Mach, especially the rejection of absolute space, surely helps explain the confusion between the two, but not only is Leibniz often misunderstood, there are influential misreadings of Newton's arguments in the scholium, influenced by the idea that he is addressing Leibniz in some way. Of course, the Principia was written 30 years before the correspondence, and the arguments of the scholium were not written with Leibniz in mind, but Clarke himself suggests that those arguments, specifically those concerning the bucket, are telling against Leibniz. That argument is indeed devastating to the parity of all relative motion, but we have seen that it is highly questionable whether Leibniz's equivalence of hypothesis amounts to such a view. That said, his statements in the first 4 letters of the correspondence could understandably mislead Clarke on this point. It is in reply to Clarke's challenge that Leibniz explicitly denies the parity of relative motions, but interestingly, Clarke does not present a true version of Newton's argument, despite some involvement of Newton in writing the replies. Indeed, the argument from the uniqueness of the rate of rotation, he argues that systems with different velocities must be different because the effects observed, if they were brought to rest, would be different. This argument is, of course, utterly question-begging against a view that holds that there is no privileged standard of rest, the view Clarke mistakenly attributes to Leibniz. As we discuss further in the companion article, Mach attributed to Newton the fallacious argument that because the surface of the water curved, even when it is not in motion relative to the bucket, it must be rotating relative to absolute space. Our discussion of Newton showed how misleading such a reading is. In the first place, he also argues that there must be some privileged sense of rotation, and hence not all relative motions are equal. Second, the argument is ad hominem against Descartes, in which context is disjunctive syllogism. Motion is either proper or ordinary, or relative to absolute space, is argumentatively legitimate. On the other hand, Mach is correct that Newton's argument of the scholium leaves open the logical possibility that the privileged true sense of rotation and acceleration more generally in some species of relative motion, if not motion properly speaking, then relative to the fixed stars perhaps. In fact, Newton rejects the possibility in the gravity on the grounds that it would involve an odious action at a distance and ironic position given his theory of universal gravity. The best explanation argument mistakenly attributed to Newton. The kind of folk reading of Newton that underlies much of the contemporary literature replaces Mach's interpretation of a more charitable one. For instance, Dasgupta, 2015, is a recent influential presentation of the following dialectic and its relation to symmetry arguments. According to this reading, Newton's point is that his mechanics, unlike Descartes', could explain why the surface of the rotating water is curved, that his explanation involves a privileged sense of rotation, and that absence an alternative hypothesis about its relative nature, we should accept absolute space. But our discussion of Newton's argument showed that it simply does not have an abductive best explanation form, but shows deductively from Cartesian premises that rotation is neither proper nor ordinary motion. That is not to say that Newton has no understanding of how such effects would be explained in his mechanics. For instance, in Corollaries 5 and 6, to the definitions of the principles, he states in general terms the conditions under which different states of motions are not, and so by implications are, discernible according to his laws of mechanics. Nor is it to say that Newton's contemporaries weren't seriously concerned with explaining inertial effects. Leibniz, for instance, analyzed the rotating body in the specimen. In short, parts of a rotating system collide with the surrounding matter and are continuously deflected into a series of linear motions that form a curved path. Though the system of Leibniz envisions it, comprised of a plenum of elastic particles of matter, is far too complex for him to offer any quantitative model based on this qualitative picture. So we had no serious alternative explanation of inertial effects. Substantivalism and the best explanation argument, the rotating spheres. Although the argument is then not Newton's, it is still an important response to the kind of relationalism proposed by the folk Leibniz, especially when it is extended by bringing in a further example of Newton's Scullium. Newton considered a pair of identical spheres connected by a cord too far from any bodies to observe any relative motions. He pointed out that the rate and direction of rotation could still be experimentally determined by measuring the tension of the cord and by pushing on opposite faces of the two globes to see whether the tension increased or decreased. He intended this simple example to determine that the project he intended in the Principia of determining the absolute acceleration and hence gravitational forces of the planets from their relative motion was possible. However, if we further specify that the spheres and cord are rigid and that they are the only things in the universe, then the example can be used to point out that there are infinitely many different rates of rotation, all of which agree on the relations between bodies. Since there are no differences in the relation between bodies in the different situations, it follows that the observable differences between the states of rotation cannot be explained in terms of the relations between bodies. Therefore, a theory of this kind attributed to the folks Leibniz cannot explain all the phenomena of the Newtonian mechanics, and again we can argue abductively for absolute space. This argument is not Newton's, neither the premises nor the conclusion, and must not be taken as historically accurate reading. However, this is not to say that the argument is fallacious, and indeed many have found it attractive, particularly as a defense of Newton's absolute space, but of Galilean spacetime. Thus, that is, Newtonian mechanics with Galilean spacetime can explain the phenomena associated with rotation, while theories of the kind proposed by Mach cannot explain the differences between situations allowed by Newtonian mechanics, but these explanations rely on the geometric structure of Galilean spacetime, particularly its affine connection, to interpret acceleration. And thus the argument goes, those explanations commit us to the reality of spacetime, a manifold of points whose properties include the appropriate geometric ones. This final doctrine of the reality of spacetime with its components, points, or regions, distinct from matter with geometric properties, is what we earlier identified as substantialism. Relationist responses. There are 2 points to make about this line of argument. First, the relationist could reply that they need not explain all situations which are possible according to Newtonian mechanics, because that theory is to be rejected in favor of one which invokes only distance and time relations between bodies, but which approximates to Newton's if matter is distributed suitably. Such a relationist would be following Mach's proposal, which we will discuss in the sequel article. Such a position would be satisfactory only to the extent that suitable concrete replacement theory to Newton's theory is developed. Mach never offered such a theory, but recently more progress has been made. Again, see the companion article. Second, one must be careful in understanding just how the argument works, for it's tempting to gloss it by saying that Newtonian mechanics, the affine connection, is a crucial part of the explanation of the surface of the water in the bucket, and if the spacetime which carries the connection is denied, then the explanation fails too. But this gloss tacitly assumes that Newtonian mechanics can only be understood in substantial Galilean spacetime. If an interpretation of Newtonian mechanics does not assume a substantialism can be constructed, then all Newtonian explanations can be given without postulating connection in an ontologically significant sense. Both Sklar and Van Frassen have made proposals along these lines. Sklar proposes interpreting true acceleration as a primitive quantity not defined in terms of motion relative to anything, but be it absolute space, a connection of other bodies. Ray 1991 points out the family resemblance between this proposal and Leibniz, suggesting that a vis viva addresses Newton's Scullian arguments. Van Frassen proposes formulating mechanics as Newton's laws hold in some frame, so that the form of the laws and the contingent relative motion of bodies, not absolute space or connection, or even an instantaneous relations, pick out a standard of true motion, namely with respect to such an inertial frame. These proposals aim to keep the full explanatory resources of Newtonian mechanics and hence admit true acceleration but deny any relation between bodies and spacetime itself. Like the actual Leibniz, they allow absolute quantities of motion but claim that space and time themselves are nothing but the relations between bodies. Some may question how the laws can be such as to privilege frames without prior space-time geometry. In response, Huggett 2006 proposes that the laws be understood as Humean best system. For a world of bodies and the relations, the laws don't reflect prior geometric structures, but systematic regularities and patterns relative motions. For obvious reasons, this proposal is called regularity relationalism. This approach is committed to the idea that in some sense Newton's laws are capable of explaining all the phenomenon without recourse to space-time geometry, that the connection and the metrical properties are explanatorily redundant. This idea is also at the core of the dynamical approach discussed in the companion article. Another approach is to consider fully spatial temporal relations. For instance, Malton 1993 discusses the possibility of a Newtonian relationalism, which has cross-temporal distance relations, distances between bodies at distinct moments of time. With such distances, relationists can capture almost the full structure of Newtonian space and time, including the affine structure required for Newton's first and second laws. Beyond Newton, in some, we have seen how historical authors from Aristotle to Newtonian and Leibniz tackle the puzzle of motion and change in physical theorizing. In a single entry on absolute and relational spacetime and motion, post-Newtonian theories, we will see how post-Newtonian authors from Mach through Einstein and other contemporary physicists and philosophers have brought new conceptual and technical resources to bear on arguably the selfsame issue. This sequel also includes a longer conclusion reflecting on the themes running through both articles. For now, we will just note that we have focused on authors who make contributions to the science of mechanics, and so a significant philosophical lacuna is a discussion of Kant's views of space and motion. Okay, so with that kind of long precursor of an overview of views on space and motion from the ancients to post-Newton and his disputes with Leibniz and leading into some modern theory, which will be a topic for further discussion as the theory goes on. Let's do now the deep dive into Newton's views on space-time and motion. And we'll see how it's going. If I'm going to call it a day after this one and do part 2 tomorrow, or if I think I'm going to be able to get through the other 2 today. Okay, so Jimmy in the chat, God bless. Yeah, I've mentioned Iamblichus. I'm not an expert in his work, but I've mentioned him in this series and other parts of my research. So God bless. Thanks for being in the chat, Jimmy. Newton's views on space, time, and motion. Isaac Newton founded classical mechanics on the view that space is distinct from body and that time passes uniformly without regard to whether anything happens in the world. For this reason, he spoke of absolute space and absolute time so as to distinguish these entities from the various ways in which we measure them, which he called relative spaces and relative times. From antiquity into the 18th century, contrary views, which denied that space and time are real entities, maintained that the world is necessarily a material plenum. Concerning space, they held the idea of empty space is a conceptual impossibility. Space is nothing but an abstraction we use to compare different arrangements of the bodies constituting the plenum. Concerning time, they insisted there can be no lapse of time without change occurring somewhere. Time is merely a measure of cycles of change within the world. Associated with these issues about the ontological status of space and time was the question of the nature of true motion. Newton defined true motion of a body to be its motion through absolute space. Those who, before or shortly after Newton, rejected the reality of space did not necessarily deny that there is a fact of the matter as to the state of true motion of any given body. They thought rather that the concept of true motion could be analyzed in terms of the specifics of the relative motions of or the causes thereof. The difficulty, or as Newton alleges, the impossibility of so doing constituted for Newton a strong argument for the existence of absolute space. In recent literature, Newton's theses regarding the ontology of space and time have come to be called substantialism in contrast to relationalism. It should be emphasized, though, that Newton did not regard space and time as genuine substances, as are paradigmatically bodies and minds, but rather as real entities with their own manner of existence, as necessitated by God's existence, more specifically, his omnipresence and eternality. Okay, and these topics are extremely complicated, so we're kind of doubling back over a lot of these ideas again and again, because as I say, these metaphysical concepts are extremely complicated, and it's almost easier to just do the math, to do the physics, than to understand the metaphysics behind it, especially in the arena of ideas where multiple truth hypothesis of conflicting theories and conceptualizations of how to understand these metaphysics. Overview of the Scholium. Today, Newton is best known as a physicist whose greatest single contribution was the formulation of classical mechanics and gravitational theory, as set out in his Mathematical Principles of Natural Philosophy, first published in 1687, and now usually referred to simply as Newton's Principia. Newton's views on space, time, and motion not only provided the kinematic basis for the monumental work, and thus for the whole of classical physics up until the early 20th century, but also played an integral role in Newton's general system of philosophy and theology, largely developed prior to the Principia. Because Newton never drafted a treatise on, or even a digest of, this general system, his stature as one of the great philosophers of the 17th century, indeed of all time, is no longer widely appreciated. A scholium at the beginning of the Principia, inserted between the definitions and the laws of motion, lays out Newton's view of time, space, place, and motion. He begins by saying that since in common life these quantities are conceived of in terms of their relations to sensible bodies, it is incumbent to distinguish between, on the one hand, the relative apparent common conception of them, and on the other, the absolute true mathematical quantities themselves. To paraphrase, absolute true and mathematical time, from its own nature, passes equably without relation to anything external, and thus without reference to any change or way of measuring time. Absolute true and mathematical space remains similar and unmovable without relation to anything external. The specific meaning of this will become clear below from the way it contrasts with Descartes' concept of space. Relative spaces are measures of absolute space defined with reference to some system of bodies or another, and thus a relative space may and likely will be in motion. The place of a body is the space which it occupies, and may be absolute or relative according to whether the space is absolute or relative. Absolute motion is the translation of a body from one absolute place to another. Relative motion is the translation from one relative place to another. Newton devotes the bulk of his scholium to arguing that the distinction between the true quantities and their relative measures are necessary and justified. It is evident from these characterizations that, according to Newton, space is something distinct from body and exists independently of the existence of bodies. There is a fact of the matter which a given body moves, and what the true quantity of motion is, and the true motion of a body does not consist of or cannot be defined in terms of its motion relative to other bodies. The first of these theses was a point of major contention in the 17th century in natural philosophy, and one assailed by Newton's critics such as Leibniz, Huygens, and Berkeley. The second was not in general dispute. Descartes, Leibniz, and Berkeley all believed that, to put in somewhat scholastic terms, the predicate X is in true motion is a complete predicate in the sense that it holds or fails to hold for any given body. Huygens, at least in his post-Principia views, constitutes a special case. Thus, for those who denied the first thesis, it was necessary to secure a definition or an analysis of what it means for a body to be in true motion and what determines the quantity of that true motion, so as to be adequate to the facts as Newton's characterization of true motion. The figures mentioned above all deem that modern motion relative to other bodies is a necessary condition for true motion, although not by itself a sufficient condition. Over the course of years, the consensus of the 17th and 18th centuries on Thesis 2 was lost sight of, and it became common to characterize Newton's opponents as denying that there is, in fact, of the matter as to whether a body is in true motion and maintaining it said that all motion is merely relative motion. Thus, modern readers expect that Newton's scholium on spacetime and motion should be read as arguing not only Thesis 1 above, but also Thesis 2, that all motion is not merely relative motion, but that some motion are true and absolute. Newton's arguments concerning motion, however, are designed to show that not that true motion is distinct from merely relative motion, which is granted by all, but rather that only feasible analysis of true motion requires reference to absolute places and thus the existence of absolute space. In particular, it has been assumed that Newton's so-called rotating bucket experiment, together with the later example of pair of globes connected by a cord and revolving around their center of gravity, is supposed to argue or provide evidence for the existence of true or absolute motion. Not only is this false, but the two cases have distinct purposes in the framework of the scholium. The rotating bucket experiment is the last of 5 arguments from the properties, causes, and effects of motion, designed to show cumulatively that an adequate analysis of true motion must involve reference to absolute space. In contrast, the example of the rotating globes is intended to illustrate how it is that despite the fact that absolute space is invisible to the senses, it is nonetheless possible to infer the quantity of absolute motion of individual bodies in various cases. The legacy from Aristotle, from antiquity. The void. The most important question shaping 17th century views on the nature of space-time and motion is whether or not a true void or vacuum is possible, a place devoid of body of any sort, including rarefied substances such as air. Ancient atomism, dating back at least to the pre-Socratic philosopher Democritus, held that not only is such possible, but in fact actually exists among the intricacies of the smallest indivisible parts of matter and extends without bound infinitely. Following Plato and Aristotle, rejected the possibility of a void, claiming that by definition a void is nothing, and what is nothing cannot exist. Aristotle's doctrines. According to Aristotle, the universe is a material plenum, finite in extent, bounded by the outermost sphere of the fixed stars. Beyond that, there is no void, empty place, since, as Aristotle defines place, the place of something is the outermost of the innermost motionless boundary of what contains it. Hence, since there are no boundaries outside the outermost celestial sphere, there are no places or space outside of it. Time, according to Aristotle, is just the measure of motion, where by motion he means change of any sort, including qualitative change, in order to define the uniformity of time. That is the notion of equally intervals of time. Aristotle was guided by astronomical practice, which in antiquity provided the most practical and accurate measures of time. He identified uniform motion with the rate of motion of the fixed stars, a choice for which he found the dynamic justification in his celestial physics. Local motion is but one species of motion, changes in place. Motion in general he defined as the actualizations of potentiality of motion, notion commonly held in the 17th century to be so obscure as to be either useless or meaningless. However, as far as local motion is concerned, there's no difficulty as to what constitutes the true or absolute motion of a body in finite geocentric universe. Indeed, elementary substances in the sublunar realm, earth, air, fire, and water, move on their own accord, either up or down toward the center, away from the center by their very nature. The celestial realm, beginning with the orbit of the moon, consists of the interlocking network of celestial spheres composed of the fifth element ether, which by its nature is disposed to a circular motion about the center of the universe, the center of the earth. If the motion of the substance is taken to be the measure of time, the celestial spheres necessarily rotate uniformly, since the net motion of an embedded sphere is the sum of its natural motion superimposed on the natural motions of the spheres in which it is embedded, and since the axes of rotation are in general set at slightly different angles in order to account for why the sun does not move on the celestial equator and the planets and the moon do not move strictly on the elliptic, the path of the sun against the fixed stars, the motion of the moons, planets, and even the sun are not necessarily uniform. However, since the spheres of the fixed stars is embedded in no other celestial sphere in motion, the motion of the fixed stars is de facto the measure of all motion. The motions spoken of so far are all natural motions of the substances in question, motions induced by the body being the very substances that it is. In contrast, other motions in which the cause of the motion is external rather than internal to the body, Aristotle subsumed under the concept of violent motion. Violent motion requires, for its continuation, the constant application of an external cause. 16th century innovations. Although Aristotle's view dominated medieval scholasticism, there occurred a renewed interest in atomism in the early 17th century. Apart from the general factors such as the Renaissance, humanism, and the Reformation, specific innovations of the 16th century made it attractive. Although Copernicus's introduction of a heliostatic system was motivated by strict adherence to Aristotle's dynamics of celestial spheres, it brought into question terrestrial physics. Galileo's telescopic observations of the surface of the moon and his discovery of the moons orbiting about Jupiter brought into question the very distinction between the terrestrial and the celestial. Moreover, the visibility of the abundance of new stars, apparently without end, suggested that the universe may in fact be without bound. Charlton in the 17th century revival atomism. An important representative of the revival atomism and its concomitant view concerning the void is Walter Charlton's Physiologia Epicuro Gesendo Charlatonia, or a fabric of science natural upon the hypothesis of Adam, founded by Epicurus, prepared by Petrus Gesendus, augmented by Walter Charlton, which appeared in English in 1654, 12 years after Newton's birth. It is a text which Newton became familiar as an undergraduate, and some of the core theses concerning time and space later put forth in the Principia and various unpublished manuscripts in Newton hand can be found in Charlton. These include that time and space are real entities, even though they fit neither in traditional categories of substance or accidents, property of a substance, that time flows on eternally in the same calm and equal tenor, while the motion of all bodies is subject to acceleration, retardation, and suspension, that time is distinct from any measure of it, like a celestial motion of the solar day, that space is absolutely immovable and incorporeal, that bodies or corporeal dimensions are everywhere, coexistent and compatient with the dimensions of the parts of space they occupy, that space, distinct from body, existed before God created the world, and that God's omnipresence is his literal presence everywhere, and that motion is the translation of a migration of body from one place as an immovable part of space to another. Charlton's argument for his view concerning time have much the same tenor as those given by Newton in the Principia. In marked contrast, though, those for empty, immense, and immutable space are quite different. Charlton appeals to the explanation of such phenomenon as rarefaction and condensation, the differences in degrees of gravity of bodies, and the numerous ways in which bodies can interpenetrate the micro levels in terms of solubility, absorption, calification, and the diverse chemical reactions. However, Charlton does not introduce the terminology of relative time, relative space, and relative places, and nowhere raises concerns regarding true absolute motion versus merely relative motion. Oddly enough, although Charlton occasionally mentions and criticizes Descartes with regard to other matters, no note of the fact is made of Descartes a decade earlier had proposed explanations in detail or an outline for just these sort of phenomena according to a system of nature in which the world is completely filled with matter and in which space distinct from body cannot exist. Descartes, it can be justly said, is the founder of the other main school of the mechanical philosophy of the 17th century, which stood in direct opposition of atomism on the issue of the possibility of a vacuum, and which adapted the Aristotelian doctrine of the nature of space, time, and motion to the New World view. Descartes' innovation. Although avowedly anti-Aristotelian in many regards, particularly on the view shared with atomists that all qualitative change on the macroscopic scale is reducible to the rearrangement and/or motion of matter on the microscopic scale, it was Descartes' ambition to carry out this program by retaining what is essentially Aristotle's notion of prime matter. The pure elements, earth, air, fire, and water, of Aristotle's physics could mutate into one another by alteration of the fundamental qualities definitive of them. There were four haptic qualities of hot, cold, wet, and dry. Because of this, there had to be something distinguishable, or at least in thought, from qualities that persist during elemental alteration. These qualities, thus substratum, is what Aristotle referred to simply as matter, or is often called prime matter, in order to avoid confusion with the macroscopically identifiable quality-laden homogeneous portions of everyday objects. Unlike atomists who attributed at least to the quality of hardness and penetrability of the ultimate particles of matter. Descartes argued that matter, or simultaneously body corpus, has no qualities whatsoever, but only quantity extension. In other words, body and extension are literally one and the same, res extensa. An immediate corollary is that there can be no vacuum, for that would require an extended region devoid of body, a manifest contradiction. The task then was to show how all apparent qualities can be explained in terms of the infinite divisibility and rearrangement of extension with respect to itself. This task was grand indeed, for its goal was to develop a unified celestial and terrestrial physics that could account equally for the ductility of metals, magnetic attraction, the tides, the mechanisms of gravity, the motion of the planets, the appearance and disappearance of comets, and the birth and death of stars. Descartes published his system of the world in 1644 as the Principles of Philosophy. Part 2 of the Principles lays out the thesis that the identity of space, extension, and matter, develops the definition of motion in the true philosophical sense, and sets out the fundamentally dynamical laws of the system. Motion, according to the truth of the matter, is defined to be a translation of one part of matter, or one body, from the vicinity of those bodies which are immediately contiguous to it, and are viewed as if at rest to the vicinity of others. In consequence, Descartes points out, each body has a single motion proper to it, in contrast to the numerous relative motions that can be ascribed to it depending on which other bodies are selected in order to determine its place. It is the single proper motion that figures in his laws of motion. Of particular importance for Descartes' entire system is that a body is in circular motion has an endeavor conatus to recede from the center of rotation. Newton's manuscript De Gravitatione. This fact, together with Descartes' contention that a body also participates in the motion of a body of which it is a part, makes it difficult to reconcile Descartes' system of the world with its definition of proper motion. Newton concluded that the doctrine is in fact a self-refuting, and that where Descartes needed to, he had surreptitiously helped himself to a notion of space independently of body, particularly in order to assign the desired degree of centrifugal conatus of the planets and their satellites as they swept about the celestial vortices of the subtle matter. The untitled, unfinished manuscript, which begin of the gravity, written perhaps a decade or more before the Principles, consists for the most part of an extensive and scathing critique of Descartes' doctrine of motion. The document, published for the first time in 1962, is well worth the study for a glimpse into the development of Newton's thinking. At a relatively young age, it manifestly embraces the doctrine of space and time, later codified in the Principia. Notable as well is that each of the 5 arguments from the properties, causes, and effects of motion advanced in the Scholium has a clearly identifiable antecedent in the gravity. This makes it clear the extent to which the Scholium is concerned to argue specifically against the Cartesian system, which Newton perceived to be only other viable contender at this time. Newton's Scholium on time, space, place, and motion. The Scholium is a clearly discernible structure. 4 paragraphs marked by Roman numerals 1 to 4 follow the opening paragraph, giving Newton characterizations of time, space, place, and motion, respectively, are summarized in the 3rd paragraph of section 1 above. If we were to extend Newton's enumeration to the remaining paragraphs, then paragraphs 5 to 12 constitute a sustained defense of the distinctions as characterized in 1 through 4. Paragraph 13 then states the general conclusion that the relative quantities are generally distinct from their respective absolute quantities, and makes comments on the semantic issue of the meaning of these terms in the Bible. There follows one remaining quite extensive, paragraph 14, which takes up the question how in practice one can ascertain the true motion of bodies, and concludes, but how we are to obtain the true motions from their cause, effects, and apparent differences, and vice versa, will be explained at length in the treatise that follows, for that is the end to which I composed it. In what follows, links have been inserted to the text of the Scholium according to the extended enumeration suggested above. Clicking on the link will open a new window in such a way that the reader can navigate back and forth between given paragraph in the text and the commentary elucidating the paragraph. Arguments for absolute time. Paragraph 5 appeals to the fact that astronomy distinguishes between absolute and relative time in its use of the so-called equations of time. This serves to correct the inequalities in the commonly adopted standard of time, the solar day, which most people mistakenly believe to be uniform. The solar day, defined as the period of time it takes for the sun to return to its zenith, varies by as much as 20 minutes over the course of a year. The standard of correction in the equation of time used in Ptolemaic astronomy was based upon the assumption that the sidereal day, the period of time it takes a fixed star to return to its zenith, is constant because the celestial sphere on which the fixed stars are located should not be assumed to speed up or slow down. With the demise of the Ptolemaic system and the Aristotelian cosmology, this rationale was no longer compelling, and at least some astronomers, most notably Kepler, called into doubt whether this rate of rotation of the Earth remained constant over the course of this year. Kepler considered that the rotation would be faster when closer to the Sun due to an excitatory effect of the Sun. Thus, the issue of the correct measure of time occupied considerable attention in the 17th century astronomy, especially because the ability to measure the rate of rotation of the Earth is equivalent to the problem of determining longitude, which for seafaring nations was critical for navigation and hence military and economic dominance. Huygens' pendulum clock provided the first terrestrial candidate for a decently accurate measure of uniform time. Newton mentions this, as well as the eclipses of the moon of Jupiter, an alternative method based on Kepler's periodic law. The invocation of the need for an equation of time in astronomy is not just an appeal to a well-entrenched scientific practice. In the course of his discussion, Newton explains why he thinks the need is justified. Although he will argue in Book 3 of the Principia that the diurnal rotation of the Earth is uniform, this is a contingent fact. It could have been otherwise. Indeed, it could have been that there are no uniform motions to serve accurate measures of time. The reason that all motion is subject to being accelerated or retarded by the application of external forces. In contrast, absolute time, which is nothing other than the duration of the perseverance of all existing things, remain the same, whether the motions be swift, slow, or null. Direct arguments for absolute space. Paragraph 6 defends the thesis of the immobility of absolute space, which, against the backdrops of Descartes, clearly means that the part of the space, just as the part of time, do not change their relation with respect to one another. Newton argues that the parts of space are their own places, and for one place to be moved out of itself is absurd. A more expensive antecedent of this argument occurs in the gravity applied specifically to time. If yesterday and tomorrow were to interchange their temporal relations with respect to the remainder of time, then yesterday would become today, and today yesterday. Thus, Newton held an interesting holistic identity criterion for the parts of space and time. The arguments from properties, causes, and effects. Newton devotes 5 full paragraphs to justifying his characterization of the distinction between absolute and relative motion. The first 3 present arguments for properties of absolute motion and rest. The next presents an argument for their causes, and the final argument for their effects. The force of these has confused modern commentators for a combination of reasons which historically are difficult to untangle. Since only those not already prejudiced by these commentaries, directly or indirectly, will find what follows unusual, it is best to defer an autopsy to those reasons until section 6, after an exposition of the arguments. Suffice it to say, for the moment, that it is common misunderstanding that in these arguments Newton intends to develop empirical criteria for distinguishing cases of absolute motion from merely apparent motion, and thereby to disprove the thesis that all motion is merely relative motion. To the contrary, the arguments take as their point of departure the assumption, common to the Cartesian and Aristotelian philosophy, that each body has a unique state of true motion or rest. Throughout the arguments, the terms true motion and absolute motion are treated synonymously. An issue is whether true motion and rest can be reduced to some special instance of relative motion or rest with respect to other bodies. In announcing at the outset of these arguments that absolute and relative rest and motion are distinguished by their properties, causes, and effects, Newton indicates his intent to show that they cannot, at least if true motion and rest are to have those features we generally associate or ought to associate with them. Argument 1 from properties, from paragraph 8. Property. Bodies that are truly at rest are at rest with respect to one another. Conclusion. True rest cannot be defined simply in terms of a position relative to other bodies in the local vicinity. Reasoning. Suppose there were a body somewhere in the universe absolutely at rest, say far away in the region of the fixed stars or even further. Whether or not this body might ever be observed doesn't enter into what follows. Clearly, it is impossible to know just from considering the position of the bodies in a region relative to one another whether any of these latter bodies maintains a fixed position with respect to the hypothetical distant body. To amplify that B be one of those local bodies, C the relative configuration over time of the set of local bodies, and A the far distant body at absolute rest. The specification of C alone fails to establish the position of B relative to A over time. In particular, C fails to establish whether B is relatively at rest with respect to A, which by the property stated above is a necessary condition for B to be absolutely at rest. Hence, specification of the local configuration C underdetermines whether or not B is at absolute rest. Thus, the conclusion it is impossible to define what it is for a body such as B to be at absolute rest, to give necessary and sufficient conditions for when it is that B is at rest, simply in terms of how B fits into the local configuration C. Argument 2 from Properties, paragraph 9. Property. If a part of a body maintains a fixed position with respect to the body as a whole, then it participates in the motion of the whole body. Conclusion. True and absolute motion cannot be defined as the translation from the vicinity of the immediate surrounding bodies, viewing the latter as if they were at rest. Reasoning. Newton first introduces two considerations that can be taken either to support or to illustrate or to amplify upon the import of the stated property. The first is that if a part of the rotating body is at rest relative to the body as a whole, it endeavors to recede from the axis of rotation. The second is that the impetus of a body to move forward arises from the combination of the impetus of its part. From the property, it follows that if those bodies surrounding a given body move, either rotationally or progressively forward as a fixed configuration, while the surrounding body is at rest relative to the surrounding ones, then the surrounding body partakes in the true motion of the group of surrounding bodies. Hence, if the surrounding bodies move truly, then so does the surrounding body, but according to the Cartesian definition of motion, which identifies a true motion of a body with its transference from the vicinity of the immediate surrounding bodies regarding the surrounding bodies to be as though they are at rest, it would have to be said wrongly that the surrounding body is truly at rest, hence the definition is untenable. Argument 3 from Properties. Property. Anything put in a moving place moves along with that place, and hence a body participates in the motion of its place when it moves relatively away from that place. Conclusion. The complete and absolute motion of a body cannot be defined except by means of stationary places. Reasoning. From the property, the relative motion of the body out of a given place is only part of the motion of the body if the place in question is itself in motion. The complete and true motion of the body consists of a motion relative to the moving place added vectorially to whatever motion the place may have. Should the place be moving relative to the place which is in turn moving, then the motion of the place must be added, and so on. Barring infinite regress, the sum must terminate with motion relative to a stationary place. Attended argument. After deriving this conclusion, Newton amplifies upon the consequence the only place that are stationary, and all of those that stay in fixed positions with respect to one another from infinity to infinity, and since these always remain stationary, they make up what Newton calls immobile absolute space. The argument from Causes. Paragraph 11. Causes. The force impressed upon bodies, the major premise is that application of a net zero, non-zero net force on a body is both a necessary and sufficient condition for either generating or altering its true motion. More specifically, impressed force is a necessary condition for generating or altering true motion, but not, as remains to be shown, merely relative motion. Application of a non-zero net force is a sufficient condition for the generation of absolute alteration of true motion, but not, as will be soon shown subsequently, merely relative motion. Conclusion. The true motion of an individual body cannot be defined as any particular sub-instance of its motion relative to other bodies. Reasoning. Newton seeks to establish the application of a positive net force to a body is neither a necessary nor sufficient condition for the generation of a motion relative to other bodies. The two lines of reasoning are given separately. We call them prong A and prong B respectively. Prong A to be established is that although an impressed force is necessary for the generation or alteration of a true motion in a body, it is not necessary for the generation of motion relative to other bodies. The reasoning is quite simple. Pick a given body and merely apply the same accelerative force to all other bodies in question, These other bodies will remain in the same relative configuration with respect to one another, but a relative motion with respect to the original body to which no force has been applied will either be generated or altered. Prong B, to be established is that although an impressed force is sufficient for the generation of alteration of the true motion of the body, it is not sufficient for the generation of motion relative to other bodies. Again, the line of reasoning is quite straightforward. Consider an arbitrary given body amongst a system of bodies and simply apply the same accelerative force to all bodies in question. Then, despite the fact that a force has been impressed upon the originally given body, there is neither generation nor alteration of relative motion with respect to the remaining bodies. The argument from effects, paragraph 12, affects the forces of receding from the axis of rotational motion, centrifugal endeavor. The main premise is that the centrifugal endeavor of bodies or parts of bodies to recede from the axis of rotation is directly proportional to the quantity of the true circular motion. Conclusion, true rotational motion cannot be defined as relative rotation with respect to the surrounding bodies. Reasoning, the line of reasoning is in fact parallel to the preceding arguments from causes, although this may not be completely perspicuous due to the fact that the correlates of the two prongs are above are here stages of single ongoing experimental situation, the so-called rotating bucket experiment, in which Newton intimates he actually performed. In order to set up this experiment, one suspends a bucket using a long cord, and by turning the bucket repeatedly, winds up the cord until it is strongly twisted, then fills the bucket with water. During the course of the experiment, the degree to which the water tries to climb up the sides of the bucket is used as a measure of the centrifugal endeavor to recede from the center. Newton uses the experiment to establish that the centrifugal endeavor is neither a necessary condition nor a sufficient condition for the existence of relative circular motion of the water with respect to the surrounding the bucket. Stage 1. When the bucket is first released, it rotates rapidly with respect to the rest of the frame of the experimenter, while the water remains at rest with respect to the experimenter. In other words, there is a rapid relative motion of the water with respect to the bucket. However, the surface of the water remains flat, indicating that it has no tendency to recede from the axis of relative rotation. Thus, the existence of the centrifugal endeavor in the parts of the body is not a necessary condition for the body to be rotating relative to its surroundings. That is, such relative rotation with respect to the immediate adjacent bodies need not produce any centrifugal endeavor in the parts of the body to recede from the axis of relative rotation. In the further course of the experiment, as the bucket continues to rotate, the water gradually begins to rotate with it, and as it does so, begins to climb up the sides of the bucket. Eventually, according to Newton, the water acquires the same rotation of the bucket relative to the lab frame, at which the point we have the following situation. Stage 2, the water in the bucket are at relative rest, yet the water has achieved its highest ascent up the sides of the bucket, indicating a maximum centrifugal endeavor to recede from the axis of the common rotation. Hence, the existence of the centrifugal endeavor is not a sufficient condition for the presence of a relative circular motion between the body and its surroundings. If a body, or rather its parts, has a centrifugal endeavor to recede from its central axis, it does not follow that there is a relative circular motion of the body with respect to its immediate surroundings. Astrophysical application. After deriving the conclusion, Newton uses the premises of the first two arguments from properties together with the premises of the argument from effects to critique the vortex theory of planetary motion. According to that theory, each of the planets, and most notably the Earth, is relatively at rest with respect to subtle matter of the celestial vortex of our own sun. Hence, according to Descartes' own definition of true motion, as well as his explicit insistence, they have no true motion. However, it is manifest that they do not maintain fixed positions with respect to one another. So according to the property invoked in the first argument, they cannot all be truly at rest. Moreover, from the property invoked in the second argument, they partake in the circular motion of the solar vortex, assuming that motion to be true motion, as Descartes implicitly assumed. Finally, because they would accordingly participate in the true circular motion of this hypothetical vortex, they should have endeavored to recede from the axis of rotation. This completes the sequence of arguments from the properties, causes, and effects of motion. The next paragraph 13 states that the cumulative conclusion of the arguments marshaled, beginning with the arguments for absolute time in paragraph 5, hence relative quantities are not the quantities themselves whose names they bear, but are only sensible measures of them, either accurate or inaccurate, which are commonly used in place of these quantities they measure. Having made his case, Newton comments on the ordinary language meaning of the terms of these quantities in order to address contemporary issues of dogma and heresy. Galileo's condemnation by the Catholic Church for asserting that the earth is in motion was still recent history at the time Newton composed the Principia. Descartes, who lived in reach of papal authority and feared similar fate, had found a clever way of espousing Copernicanism without falling prey to the accusation of heresy. According to his definition of motion, properly speaking, he contends that the earth is truly at rest. In Newton's system of the world as set out in Book 3 of the Principia, the earth patently moves absolutely. In anticipation, Newton indicates how to reconcile with Scripture by observing that if usage determines the meanings of the words, then in ordinary discourse, including the Bible, the terms time, space, place, and motion are properly understood to signify relative quantities. Only in specialized and mathematical contexts do they denote the absolute quantities. Keep in mind Newton's title, The Mathematical Principles of Natural Philosophy. He proceeded to chastise Descartes on two accounts. First, for doing violence to the Scripture by taking them to refer to absolute quantities, and second, for confusing the true quantities with their relative measures. Discriminating in practice between absolute and apparent motion. Having argued his case that true motion consists in motion with respect to absolute space, and thus having dealt to his satisfaction with the metaphysics of motion, Newton turns in the final paragraph of the Scholium to his epistemological strategies available on his account. On an Aristotelian and Cartesian account, one can directly observe the allegedly absolute motion of body if both it and its immediate surroundings are visible. In contrast, because of these parts of absolute space are not directly accessible to the senses, it is very difficult, Newton confesses, to ascertain the true motion of individual bodies and to discriminate them in practice from the apparent motions. Nevertheless, he remarks in a rare moment of wit, the situation is not entirely desperate. Evidence is available in part from apparent motions, which are the differences of true motions, and in part from the forces, which are the causes and effect of true motions. Newton illustrates with an example. Imagine a pair of globes connected by a cord, revolving around their common center of gravity. This endeavor of the globes to recede from the axis of motion is revealed by the tension of the cord, from which the quantity of circular motion can be estimated. Furthermore, whether the direction of their revolutions is clockwise or counterclockwise can be detected by applying forces to the opposite faces of the globe to see whether the tension of the cord increases or decreases. All this can be done in empty space where no other bodies are present to serve as points of reference. Suppose now that in addition to the globe, there is a second system of bodies maintaining fixed position with respect to one another, for example, the fixed stars. If the two systems are in a state of relative motion, one cannot gauge from just the relative motion which if either is at rest. However, from the tension of the cord connecting the globes, one can establish whether the relative motion is due entirely to the absolute rotation of the system of globes. Supposing so, the second system of bodies can then be exploited to provide an alternative technique for determining whether the globes revolve in a clockwise or counterclockwise direction. One simply consults the direction rotating relative to the stationary system. At this point, Newton cuts off the Scholium, explaining that the whole point of having written the treatise to follow is to show how to infer the true motions from their causes, effects, and apparent differences, and conversely the causes and effects from either the true or the apparent motions. Common impediments to understanding the Scholium. As remarked in section 5.3 above, the purpose of the arguments from properties, causes, and effects has been widely misunderstood in both the historical and philosophical literature, and as a consequence, so too the relation of these to the example of the revolving globes in the final paragraph. Some diagnosis as to why might help those readers already steeped in the tradition to overcome certain prejudices they bring to the Scholium, and may help to serve further illuminate the framework in which Newton and his contemporaries struggle with the problem of motion. What the major impediments are. Newton's stated intention that the Scholium is to maintain that absolute space-time and motion are generally distinct from their relative counterparts. For the case of space, this clearly amounts to arguing that the existence of an entity distinct from body in which bodies are located, something denied by relationalists. Similarly, for the case of time, this involves arguing the existence of an entity distinct from the succession of particular events in which the events are located, again, something denied by the relationists. It may seem then, as a matter of course, that for the case of motion, Newton should argue for existence of something denied by relationists, presumably absolute motion. It would amount to a virtual petito principii, where Newton, to rest a case for absolute motion on the existence of absolute space, Hence, one would expect him to appeal to the various physical phenomena that might provide independent warrant. Now, it is well known that Newton's laws satisfy the principle of Galilean relativity, according to which there can be no experimental test to determine whether a system is at rest or in a state of uniform rectilinear motion. However, Newton's laws do support distinction between inertial and non-inertial motion in that they predict in non-inertial frames the appearance of so-called fictitious forces. For instance, centrifugal forces in rotating frames, resulting in the tendency for bodies to recede from the axis of rotation. Since this is exactly the effect involved in a rotating bucket experiment, it is tempting to interpret Newton as marshalling. It is a case in which the phenomenon suggests independent warrant for existence of absolute motion. Moreover, since the same effect is operative in the example of the revolving globes, it is hard to see why the example does not serve the very same purpose. In fact, in his famous critique of Newton in The Science of Mechanics, Ernst Mach, in quoting from the Principia, cuts out all of the intervening text to make it appear as though the two are but varying examples in the development of a single argument. Finally, in the choice of language in Mott's 1729 translation, which is the basis for the most widely available 20th century English translation by Cajori, tends to reinforce the presumption that the arguments from properties, causes, and effects seek to identify phenomena that empirically distinguish absolute from merely apparent motion. In the Cajori version, the conclusion of the first three arguments, the arguments from the properties of motion and rest, read, it follows that absolute rest cannot be determined from the positions of bodies in a region. The true and absolute motion of a body cannot be determined by the translation of it from those which are only seem to rest. Wherefore, entire the absolute motion can be no otherwise determined than the immobile places. Thus, in attempting to assume that both the argument from causes and the argument from effects are likewise concerned to identify an empirical signature of absolute motion by which it can be distinguished from merely apparent motion, regarding the arguments in this fashion, only the arguments from effects, which deal with the centrifugal effects of circular motion, appear to help Newton's cause a commonly registered complaint. Why they are indeed impediments. It will be more illuminating to respond to these in reverse order. It is a fact of Mott's translation of the Latin verb definire, passive indefinite, is rendered occasionally as be determined rather than to be defined according to the 17th century English use. Either choice is acceptable. In appropriate context, the two function as synonyms, as in the Euclidean axiom, 2 points determine a line. Mott's practice conforms with this. The conclusion from the argument from effects definire is translated as to be defined, as paragraph 12, and therefore this endeavor does not depend upon the translation of the water in respect to the ambient bodies, nor can true circular motion be defined by such translation. If one now goes back and substitute be defined for be determined into the conclusion for the arguments from the properties quoted above, they take on to the modern era different meaning. They make claims as to what constitutes an adequate definition of the concepts of true or absolute motion and rest. We have already seen paragraph 13 signals the conclusion, not just the argument from properties, causes, and effects, but the direct arguments from absolute time and absolute space as well, which, although Newton establishes the ontological distinction between the absolute and relative quantities, the next paragraph in which the globes are introduced concerns a different epistemological issue, which would be apparent if it were not for another artifact of the Mott translation, this time involving the Latin verb distinguere. Newton uses the word again and again, almost thematically, in characterizing and arguing for the ontological distinction between the absolute and the relative quantities, and Mott readers renders it in English as to distinguish. Unfortunately, the English verb appears in the Mott translation one or more times at the start of the final paragraph. It is indeed a matter of great difficulty to discover and effectually to distinguish the true motions of particular bodies from the apparent, but in Latin the word distinguere is nowhere to be found. Rather, the sentence reads, thus, to the Latin reader, it is clear that Newton is moving on to a different consideration. What has been said in connection with these suffices against the false expectations developed. However, there may remain some sense that even on a proper reading, Newton tried to bluff his way past the principle of Galilean relativity. Newton indeed acknowledges the principle, though not by name, in Corollary 5 to the law of motion. The motion of bodies in a given relative space are the same amongst themselves, whether the space is at rest or moves uniformly in a straight line without uniform motion. And there's no reason to think that he did not appreciate the limitation that poses for experimentally differentiating between absolute rest and uniform motion in a straight line. A particular instance of Corollary 5 is the solar system as a whole, assuming the absence of external forces. It follows from Corollary 4 to the laws that the center of gravity of the solar system is either at rest or moves uniformly in a straight line, but which, because of the Corollary 5, when Newton wishes to attribute a definite state of motion to the center of mass of the solar system in Book 3, he must introduce the hypothesis that the center of the system, the world, is at rest. Should this not be some source of embarrassment? Apparently not. Immediately following the hypothesis, he writes, "This is conceded by everybody, although some contend it is the earth, others the sun, that is at rest at the center. Let us see what follows from this." According to Newton, the attribution of a state of absolute rest to one or other of these bodies is universally taken for granted. What does confound all conventional wisdom in what follows is that neither the earth nor the sun is at rest, but rather the center of gravity of the solar system. Although arguing that absolute space and absolute time are distinct from any relative spaces and relative times involves, in each case, arguing for the existence of an additional entity, it does not follow that in arguing that absolute motion is distinct from relative motion, Newton is obliged to argue yet another existent claim. Unfortunately, the term absolute motion is prone to be read in two distinct ways. On one reading, it means, as a matter of stipulative definition, change of absolute place. In this sense of absolute motion, the existence of absolute motion, or more precisely, the possibility of the existence of absolute motion, follows immediately from the existence of absolute space and absolute time. As indicating before, nothing further needs to be said. On the other reading, absolute motion is synonymous with true motion, and as we have just said, Newton finds no reason to doubt that his audience does not grant that a body is either truly at rest or truly in motion. The venerable tradition that takes motion and rest to be contraries has yet to be questioned, so it's not incumbent upon Newton to make a case for the reality of absolute motion in the sense of true motion. What is incumbent is for him to argue that true motion is change of absolute place, and that is the purpose of the arguments from properties, causes, and effects. Newton's legacy. Newton's views on space-time and motion dominated physics from the 17th century until the advent of the theory of relativity in the 20th century. Nonetheless, these views have been subjected to frequent criticism, beginning with contemporaries such as Leibniz and Berkeley, and continuing on to the close of the 19th century, most notably in Ernst Mach, whose writings influenced Einstein. In the early 20th century, Newton tended to be cast as a metaphysician dogmatist by the early philosophical interpreters of relativity, in particular by Hans Reichenbach. Unfortunately, that stigma has tended to linger. More recent scholarship reveals a more sober picture of why Newton felt fully justified in positing absolute space, absolute time, and absolute motion. Moreover, the novel feature of special relativity, the rejection of absolute simultaneity, something that never occurred to any of Newton's earlier critics, necessitated only by the absolute space and absolute time be replaced by an absolute spacetime, Minkowski spacetime. And although Einstein's development of general relativity was in large part motivated by a desire to implement a general principle of relativity, to wit, that all motion is relative motion, that it succeeds in doing so was questioned shortly after the theory was introduced. As for the question of the absoluteness of spacetime and general relativity, it no longer has the character of something which acts without being acted upon. As Einstein himself pointed out, the spacetime metric tensor not only encodes for a spatial temporal structure, but also represents the gravitational potentials and thus gravitational energy. By Einstein's famous equation for the equivalence of energy and mass, it follows that the gravitational field possesses mass only since gravitational energy cannot be localized in terms of energy density tensor, but if possessed by the field holistically, neither can this mass be localized. Thus, philosophical controversy as to whether spacetime can exist without matter becomes tendentious according to whether one counts the gravitational field as something material or not. Thus, the question whether the revolution in our views about space and time in the last century vindicates Newton's critics as more philosophically astute becomes a misplaced one. The distinction between what counts as matter in contrast to empty space presupposes that earlier debates has been eclipsed by possibilities undreamt of before the introduction of modern field theory and relativity. Okay, so I think I'm going to leave it there for today, because it's probably close to another 3 to 4 hours of reading, which unfortunately I just don't have strength for. So, God give me strength. A lot of research, a lot of this is tedious and technical. So, yeah, I hope to tomorrow to go over again. Um, Hopefully, I'll have time to go over some of this tonight, and that will allow me to review some of this and have some hopefully more intelligent things. Yeah, God bless you too, Jim. We appreciate you being in the chat. You're the only one left, Mr. Newton. I mean, Mr. Boston, the last Australian, Matthias. Anyone who's here, appreciate that. Hope this is useful to you also. So yeah, a lot of information here, a lot of complicated stuff to go over, and I'm not exactly sure what to make of it. I got to piece it together in my mind. You're just doing my due diligence. I've talked a lot about um, the the Galilean, Descartes, uh, Newtonian revolution in science, the changing the conception of universal laws described by mathematics, that has become extremely prevalent in modern times, and even reduced from Bertrand Russell and Frege, Wittgenstein, to reduce all philosophy to some sort of logical notation, to the logical empiricist, the Vienna Circle. So a little bit overwhelming right now, but just keep on doing the due diligence. Hopefully tomorrow I'll have a little bit more time and energy, so I'll draw some conclusions, and we'll go over the Principia in detail. We'll look at the in detail Newton's Principia, and then we'll look at Hume's Newtonianism and anti-Newtonianism, where we get kind of the modern empirical method of the complete formulation of the philosophical implications of modern empiricism, of the Newtonian method, to all forms of philosophy. So yeah, I still hope to go back. So I'm going to go backwards. Probably next in the series, I'm going to go to the French. I'm going to look like Descartes, Arnauld, Gassendi, Mellenbrock, and maybe one other. So we'll look at like the Descartes and some of his disciples at the time, and then maybe we'll do a metaphysics one, looking at Cartesian philosophy, and then I'm not sure from there. So all these are huge topics, and it's a little bit overwhelming, but just to go through, get these ideas, become conversant in it, and hopefully get a community of people interested in these ideas to put it to use. Maybe get back to my writing. Going to connect this to my multiple truth hypothesis, and hopefully this will be useful to all aspects of just the mental acuity, relating to the science of expertise and other things I'm talking about on Week in Review, but just specifically the metaphysical, philosophical background to anything that we do, and moving forward to the due diligence to will hopefully be coming out with real efforts in my multiple truth hypothesis. So God bless. Thanks for tuning in. Hopefully I'm going to schedule tomorrow, hopefully about 2 or 3 o'clock tomorrow, and we'll finish out the last 2 sections. So thanks for tuning in. God bless.